some time for climbing a little bit, but okay. But now it's skiing time, actually. It's not anymore climbing time. How is it in the, yeah, you are in a flat area, right? So
it's running time all the time.
Running time, good. I like running also. Very happy to see you. I was actually, yeah, I'm really sorry I couldn't follow live the other days. I have seen some of the videos actually.
So I will go back to screen share for Lingal's talk.
Yeah, you can try, Pratyush. Omar is also here. Let's start the recording. Starting the recording. Yeah.
So, Nishant, shall we start?
Yeah, we can start actually. Yeah, yes. Yes, Padmash, go ahead.
Yeah. So, okay, good evening all. So, welcome to the penultimate and the final talk session of RARE 2021. So, we have had some stimulating discussions in the last 7 sessions that has concluded. So, for this particular sessions, we have 4 speakers. So, Dr. Lingal Wang, Professor Cecilia Clementi, Professor Amal Varsil, and Professor Harish Vasist. So we have each sessions for 30 minutes duration, and we can take up 5 minutes of discussions for each of the session. So we'll start our first session with Professor Dr. Wang. So unfortunately, I think Professor Dr. Lingal Wang is away and he has sent us a recording. So we'll start with the recording of the session. And in case if he's there towards the end of the talk, we will take up the discussion session or we'll write to him for the discussion. Fine. I hope that is fine, Nishan. Okay, all good. So shall we go ahead with the
thank you. Yes, yes, Pratyush, please.
First, thank the organizers for arranging the conference and for inviting me to speak here. I'm happy to present some recent work at Schrödinger for protein ligand binding field calculations. Schrödinger is a scientific leader in computing chemistry, providing software solutions and service to advance drug discovery projects. We are particularly interested in any computing method that has potential to transform drug discovery projects. Today, I'm going to talk about our methods for protein ligand binding field calculations. A little bit background about why we are interested in this problem. As we all know, drug molecules achieve their therapeutic effects through binding to the protein binding pocket, either blocking the protein function or changing their conformations to alter the downstream single transduction pathway. In either case, the efficacy of drugs are correlated with their binding affinity. As a result, the major objective of small molecule lead optimization, one of the most expensive stages in drug discovery projects, is to identify molecules with improved binding potency while maintaining a list of other ligand properties to achieve the safety and biological efficacy. Therefore, accurate calculation of protein binding affinity is of key importance in computational drug discovery. Atomic's model, affinity calculation, is the most rigorous method to calculate protein ligand binding affinities. At Schrödinger, we initially were focused on relative binding affinity calculations between generic ligands, following the summary cycle shown here. FEP is a rigorous theory, but the accuracy is critically dependent on 2 aspects. First, we need an accurate force field to describe the atomic level interactions between proteins, ligands, and water molecules. Second, we need an efficient sampling method so that the relevant and the important conformation space for the 2 physical endpoints can be finally sampled in a relatively short MD estimations. For large biomolecules like proteins with many local minima separated by a high energy barrier, using brute force MD estimations, the system will stay trapped in the local minima corresponding to the initial geometry and configuration. And the calculated binding affinity using brute force MD will be systematically dependent and biased towards the initial configuration, introducing large errors in the calculated binding affinity results. And at Schrödinger, we are addressing both the force field accuracy and the sampling efficiency problems. With over a decade of efforts, we have developed by far the most accurate force field, OPS4, for small molecules and proteins. and we are continuing our effort to further improve the accuracy for the force field. At the same time, we have worked out a number of methodological improvements that dramatically improve the efficiency to sample the relevant conformation space associated with ligand binding, including the ligand and protein side chain conformation changes and water relaxation in the deeply buried binding pocket. Combining those efforts, we have developed by far the most accurate assay F+ for protein ligand binding fingerling calculations, which has been used as a benchmark for other methods development. In the initial paper published in 2015, we validated F+ method on a set of 8 pharmaceutical interesting drug targets covering a diverse chemical space with more than 200 unique ligands. And the calculated binding affinity are highly correlated with experiment, with overall root mean square error of about 1.1 kcal per mole, and the errors are roughly Gaussian distributed. After that, we have introduced a number of novel methods that dramatically improve the accuracy and expanded application domain of fingerling calculations, enabling highly complex and diverse populations to be modeled with very high accuracy, including scaffold or co-hopping modifications, macrocycle populations, charge populations, reversible and irreversible covalent inhibitions, and so on. And at the same time, with the continuous improvement in the force field accuracy, the reliability and accuracy of calculations has also been further improved. In the next few minutes, I'm going to present and focus on a few novel methods that dramatically expanded the application domain and improved accuracy of fingerling calculations. Historically, FEP method was designed for relatively small perturbations, for example, mutating the methyl group into a hydroxyl group, or adding a fluorine atom on an aromatic ring, or changing the nitrogen linker in the molecule into an oxygen linker. Accurate and reliable calculation for those type of perturbations already allows a large number of molecules to be tested. And as we saw already, it already generated a large impact in real discovery projects. However, the impact of FEP will be much limited if we restrict ourselves to those kind of very minor and modest modifications. In drug discovery projects, chemists would like to explore a much diverse chemical space and very often consider very challenging populations. For example, if the core of the molecule has certain atomic toxicity issues, they may want to introduce additional ring or to change the size of the ring in the core of the molecule. Those are so-called scaffold hopping or co-hopping modifications. So how to calculate the affinity change for a co-hopping modification? Another example, for targets that do not have deep binding pockets, blocking the protein-protein interface is a very viable strategy. And the macrocycles are very good candidates to block protein-protein interface. And how to calculate the affinity change to cyclize a linear molecule into a macrocycle. Both type of relations are very challenging for conventional method. And in the following, I'm going to explain the unique challenges associated with those relations and our methods to address those. So co-hopping, as mentioned earlier, in drug discovery projects, chemists often would like to consider populations that change the size of the ring or introduce additional rings in the middle part, in the core part of the molecule. Those type of populations are called scaffold hopping or co-hopping modifications. Well, it might be relatively straightforward to revise the synthetic route to make a molecule with a different R group. Synthesizing a molecule with a new core may require months of chemistry effort. And since the topology of the pharmacophore is modified in a co-hopping modification, the majority of co-hopping attempts failed to provide any valuable matter to the project because the majority of co-hopping attempts resulted in a molecule that is not active. But even that, co-hopping is often attempted in drug discovery projects because very often it is the only viable strategy to resolve a particular enemy toxicity issue. And also the novel IP generated by co-hopping makes it even more attractive. So therefore, accurate calculation of the affinity change for co-hopping modification will enable the chemists to pursue co-hopping modifications with confidence that the resulting molecule is potent enough and useful for the project. So co-hopping is a novel topic with no earlier research on this area before. And here I will use one example to explain the fundamental difference between the conventional R group modification FEP versus the co-hopping FEP. For R group modification FEP, for the example shown here, mutating from the chlorine atom into a hydrogen atom, if we retain all the leftover, the bounded stretch interaction between all the leftover dummy atom and the rest molecule, we can easily see that the ensemble of configurations for the mixed topology molecule is the same as for the target physical molecule. In other words, the bounded stretch interactions between leftover dummy atom and the rest molecule won't affect the ensemble of configurations. So therefore, we do not need to calculate the finish to form or to break a covalent bond. But this is not the case for co-hopping FEP. For the example showing here, to mutate from a fused ring into a linear molecule, if we retain all the bounded stretch interaction between the leftover dummy atom and the rest of molecule, we can easily see that the ensemble of configurations sampled for the mixed topology molecule with the dummy atom and the bounded stretch interaction will be different than the real physical target molecule. For the physical molecule, without the dummy atoms, it can access many different conformations through rotation around this two rotational bond. By comparison with the dummy atom and the bounded stretch interactions, the ensemble of configurations will be much limited. So therefore, in co-hopping FEP, we have to explicitly calculate the finish to form or to break a covalent bond, which was believed to be extremely difficult or even impossible. There are two unique challenges associated with the calculation of the finish to form or to break a covalent bond. The first one is singularity, numerical instability problems. So in almost all the commonly used molecular mechanics force field, the bounded stretch interactions are represented by a harmonic potential. And using the conventional FEP to scale the potential by a coupling parameter lambda, we can easily see that the derivative of the finish with respect to the coupling parameter lambda diverges and is undefined when lambda approaches zero, introducing singularity and numerical instability problems in the finish calculations. The second challenge is associated with the convergence of the finish. So when lambda equals 1, with the bounded stretch interaction fully turned on, the distance between two atoms approximately follow a Gaussian distribution, approaching delta distribution with a very strong force constant. By comparison, when lambda equals 0, when the bounded stretch interaction is turned off, the distance between the two atoms approximately follows a flat distribution. Those two distributions differ so much that it has very, very little phase space overlap. And it's very difficult to design an intermediate state that has sufficient phase space overlap with both physical endpoints. And to address those challenges, we have invented a novel functional form, which we call the soft bond potential. The formula shown here, we can see that when lambda equals 1, this equals 0. So this potential recovers the harmonic potential used for the bounded stretch interaction in conventional force field. When lambda equals 0, this potential goes to 0. And for lambda values between 0 and 1, the potential changes slowly from harmonic to 0. Both the first and second derivative of the potential with respect to lambda and R are continuous and valid. And through rigorous statistical mechanical derivations, we prove that using this potential, it solves the singularity and numerical instability problems associated with the calculation of the finish to change, to form, or to break a covalent bond, and also resolve the convergence issues in the calculations. The soft bond potential for co-hopping FEP implemented in FEP tasks allows reliable and accurate calculation of the finish for co-hopping modifications. So here's one example. Receptor is EZH2. The company Epsilon just has the first drug approved for this target. The 4 molecules shown here are close analogs of the drug molecule. So for molecules 22 and 27, it has a fused ring in its part of molecule. For the corresponding molecule 29 and 31, the fused ring is opened to form a single ring. For the perturbation, to open the fused ring into the single ring for 22 to 29, and also from 27 to 31, the co-hopping FEP calculated binding affinity is in very good agreement with the experiment. One important property and interesting for the system is the strong line activity effect. In particular, with the 5-member ring in the tail of the molecule, opening the fused ring into the single ring only modestly increased binding potency by about 0.5 kcal. By comparison, with the 6-member ring in the tail of the molecule, the same perturbation to open the fused ring into the open ring dramatically improved the binding potency by about 2 kcal. And the strong line additivity effect is also accurately captured by co-hopping FEP. Another example, receptor space 1. For the perturbation, they introduce additional ring to mutate from the fused ring into the bridged ring. The co-hopping FEP calculated binding affinity is also in very good agreement with the experiment. And in this paper, we have validated co-hopping FEP on a set of 6 pharmaceutical interesting drug targets covering many different co-hopping perturbations with diverse chemical space. Again, the co-hopping FEP calculated binding affinity is in very good agreement with experiment with overall RMC of about 0.5 kcal, R squared is 0.81. Very recently, we have also extended the same soft bond potential to address another type of very challenging perturbations, the macrocycle perturbation. Macrocycles occupy a unique region in chemical space, bridging between small molecules and large biomolecules. Macrocycles are usually very difficult to synthesize. However, due to their unique ability to balance many different drug properties, including potency, selectivity, membrane permeability, and bioavailability, macrocycles are often considered in drug discovery projects, particularly for targets that are difficult to drug by small molecules. In macrocycle drug discovery, there are 2 most frequently asked questions. The first one is whether a macrocyclation strategy to cyclize a linear molecule into a macrocycle will improve the binding potency. Second one is, what is the optimal linker size and chemical matter for cyclization? Both perturbations are very challenging for conventional FEP method. And using the same soft bond potential and adjustment parameters specific for macrocycles, FEP plus can accurately evaluate both perturbations. And in this paper, we have validated the macrocycle FEP on a set of 7 drugs, interesting drug targets covering many different macrocycle perturbations with diverse chemical space. And again, the calculated binding affinity is highly correlated with the experiment with overall RMC of about 1 kcal, R squared is 0.7. The accuracy of FEP plus calculations has been independently validated by a large number of pharmaceutical and biotech companies. For example, Bayer has applied FEP plus on their internal very challenging data set, including perturbations that cyclize a linear molecule into macrocycle. And the calculated binding affinity, again, is in very good agreement with the experiment, with the results published in this paper. Combining all those improvements, FEP plus allows very complex and diverse molecules to be modeled with very high accuracy. For example, for a set of HP90 inhibitors shown here, from ligand 69 to 65, the charge in the side chain is removed and the different charge was introduced in the macrocycle, and the overall effect is accurately calculated by FEP plus. Another example, from ligand 65 to 68, a ring was introduced in the side chain, and also the size of macrocycle is modified. Again, the overall effect is accurately calculated by FEP plus. In 2017, we spent another effort and collected FEP plus performance on about 90 projects that we were able to have access to. The majority of them are prospective studies. Some come from our customers. And the overall performance is showing here. The means unsigned error for the aggregated data is less than 1 kcalmol. For the majority of projects, for more than 80%, the mean signed error is less than 1 log unit. In agreement with the accuracy seen in retrospective validation. However, we can also see that for a very small percent of projects shown here, the mean signed error is approaching about 2 kcalmol, much less accurate than other systems, and also making it not very useful for small molecule need optimization. So what are the reasons for those outliers? After a careful investigation of those outlier cases, we have identified 3 areas that can further improve the accuracy and robustness of protein binding calculations. A, improving the sampling of water relaxation in the deeply buried binding pocket. For example, for the HP90 system shown here, there are 2 water molecules in this deeply buried binding pocket. For perturbation, they introduce different chemical group to displace those 2 water molecules. If the perturbation was initiated without the water in the binding pocket, there will be an artificial dry region in the binding pocket, even in the presence of a smaller ligand. If FEP was initiated with those 2 water molecules in the binding pocket, the water molecule will remain trapped in the binding pocket, even in the presence of bigger ligand. In either case, large errors will be introduced in FEP. And by improving the sampling of water relaxation in the deeply buried binding pocket, the accuracy of FEP can be dramatically improved. B, rigorous sampling of the pronation and tautomeric state of ligand and protein residues in the binding pocket. For many systems we are interested in, like the example shown here for the base systems, the pronation and tautomeric state of ligand is coupled with that of the residues in the binding pocket. And a large portion of 5P plus outlier cases are due to improper assignment in the pronation tautomeric state in the ligand or protein residues in the binding pocket, or failure to identify the change of pronation state associated with ligand binding. So therefore, by rigorously modeling the pronation tautomeric state of the titratable residues and ligands in the binding pocket, 5P plus accuracy can be dramatically improved. C, improve the sampling of ligand-induced protein conformation changes. For example, for the HP90 system shown here, in the presence of smaller ligand, this part of protein is adopting a looping conformation pointing towards ligand with a very small R group extension, adding a 5-member ring in this part of ligand. It pushes the looping to adopt a helical conformation. The looping to the helical conformation protein cannot be sampled in a very short amplification, causing large errors in the class results. Therefore, by improving the sampling of ligand-induced protein conformation changes, the accuracy of French calculations can be dramatically improved. And over the past few years, we have been working on a number of novel methods that address those challenges and further improve the accuracy and robustness of protein ligand binding French calculations. For example, to improve the sampling of the water relaxation in deeply buried binding pocket, we have implemented the ground canonical Monte Carlo GCMC method to enhance the sampling of water relaxation. The GCMC enabled FEP dramatically improve the protein ligand binding calculations. So for a large aggregate of dataset covering many different protein targets, focusing on perturbations that displace water molecules in the binding pocket, the GCMC-enabled FEP got much improved results with errors much smaller than the conventional FEP. To improve the sampling of ligand and the protein residue pronation tautomeric state, we have been working on a general constant pH method. And the constant pH method calculated protein PK results are in very good agreement with experiment. And we are in the process of integrating the constant pH into protein ligand binding calculations. And to improve the ligand-induced protein conformation changes, we have been working on a novel method that can accurately calculate the phase difference between the different conformations of the protein. For the HP90 example I mentioned earlier, for the perturbation that introduce additional R group, using the looping conformation of protein, the bigger ligand has severe steric clash with the looping conformation and splitting crest. By comparison, using the helical conformation of protein, the bigger ligand was predicted to bind by about 6 kmol stronger than the smaller ligand, a severe overestimation as compared experiment of -3.2. Using protein conformation FEP, the looping conformation was predicted to be favored by about 2.6 kmol in the presence of a smaller ligand. And combining protein conformation FEP and ligand population, the bigger ligand was predicted to bind by about 3.4 kmol stronger than the smaller ligand, in very good agreement with the experiment. And we are in the process of automating this process and potentially release this in our future version of the product. In addition to relative binding affinity calculations with the main use case in small molecule lead optimization, we have also been working on absolute protein binding affinity calculations to improve the hit rate in virtual screen. So as we all know, for any drug discovery projects, after the target has been selected, the first step is to explore a diverse chemical space to identify as many lower hits as possible. Without the initial hit and lead, we cannot use relative binding affinity FEP to improve the ligand properties. As a current best practices, empirical scoring function is used in virtual screening to dock a large number of compounds. And due to the limited accuracy in empirical scoring function, the average hit rate is only about 1%. So therefore, the project team needs to purchase a large number of compounds to identify a few hits. For molecules that are not readily purchasable, making them can be very expensive and time consuming. And even for compounds that are readily purchasable, setting up the biological assay to confirm their biological activity can sometimes be very expensive and time consuming. So therefore, any methods that can improve the hit rate is very valuable. And for that purpose, we have worked out absolute protein binding affinity FEP, the so-called ABFEP, to enable the scoring of molecules with diverse scaffolds in different chemical space. And by rescoring the top compounds in virtual screening by ABFEP, the hit rate can be dramatically improved, as you will see from the later discussion. So the thermodynamic cycle for absolute binding FEP is shown here. So we need two explanations. In the solvent neck, starting from the physical ligand, interactions between ligand and the water is slowly turned off to become a dummy ligand. For the complex neck, starting from the dummy ligand with a set of restraints to put the ligand in the binding pocket, interactions between the ligand and the environment is slowly turned on, followed by relaxing the restraint potentials. The purpose of the restraint potential is to keep the relative position and orientation of ligand with respect to protein binding pocket to prevent it from drifting away from the binding pocket in intermediate long windows. And the final difference between the unrestrained dummy ligand and the restrained dummy ligand in the complex is calculated by an analytical formula. We have validated our ABFE method on a large number of systems, including small fragments binding to different protein targets, the entire 8 systems from the JAX publication, and also the respective virtual screen dataset, which I will discuss in detail later. The performance on the 8 systems from the JAX publication is shown here. The ABFEP average, the overall RMC is about 1.11 kcal, and the overall RMC average R squared is 0.61 kcal, both comparable to the relative binding affinity FEP results. In addition to the JAX dataset, we have also validated ABFEP in the context of hit discovery. Here's one example. Receptor is pseudo-kinase domain of JAK2 receptor. Jorgensen group performed virtual screening on about 3.8 million drug-like compounds from Zinc-15 database using GLIDE. Then from the top 1,000 compounds based on visual inspection of the binding pose, rescoring with XP, GOLD, and MMGDSA, they have identified 30 compounds to be purchased and tested. By eye, those 30 compounds have very good binding pose very good interactions with the protein binding pocket. They have comparable or even better docking scores than the 13 known JAK2 inhibitors. Therefore, they have very high confidence that at least some of those compounds will bind to JAK2. So they expect to discover some novel hits from this exercise. Of those 30 compounds, 27 were successfully assayed and tested. And to their very surprise, none of them showed detectable binding to JAK2. So it's a complete failure for word screening. But this is a very good test set to test ABFEP's ability to improve the hit rate and to differentiate actives from inactives. So we run ABFEP on those 40 compounds, including the 13 known JAK2 inhibitors and 27 challenge decoys. Here are the results. Using the top poses from GLIDE as initial pose for ABFEP, the enrichment curve from ABFEP score versus GLIDE is shown here. As mentioned earlier, GLIDE score cannot differentiate the actives from inactives. The majority of the inactives has even better docking score than the actives. So therefore, the AUC for GLIDE is very poor, 0.03 and 0.11 respectively. By comparison, ABFEP can clearly differentiate the actives from the inactives. The AUC is improved 0.8. In Jorgensen's paper, they also performed very expensive metadynamic explanations to pull the ligand from the binding pocket. And the stability of the ligand from the metadynamic explanations was shown to be able to better differentiate actives from inactives. The ABFEP performance is even better than metadynamics. So for some of the known JAK2 inhibitors, the crystal structure is available. So we also tested the sensitivity of results with respect to the initial binding poses for ligands. For ABFEP, the better ligand poses translated into better accuracy, and the AUC is improved 0.95, almost perfect. The actives stand out from those ABFEP calculations. By comparison, for other measures, the results are not very sensitive to ligand pose. So for those 13 known inhibitors with experimental binding affinity available, we can also compare the ABFEP results with experiment. ABFEP results are highly correlated with experimental binding affinity for those known JAK2 inhibitors. Using the top poses from GLIDE, the R-squared is 0.41, while using the crystal poses when available, the R-squared improved to about 0.7. So here's a summary of my presentation. So with many years basic research in force field and enhanced sampling methods development, we have developed the F+ method that can accurately and reliably calculate protein binding affinity and enable very accurate and reliable calculations for very challenging populations, including co-hopping or Stanford hopping modifications, macrocycle populations, covalent inhibition, and also the charge populations from the benzene PP, which I didn't mention in this presentation. And both retrospective testing and prospective performance has demonstrated the high level of accuracy in F+ calculations for protein binding affinity. In addition, through a careful analysis of a large aggregate of F+ data, we have identified 3 areas that can further improve the accuracy of protein binding affinity calculations. A, improving the sampling of water relaxation in the binding pocket. B, rigorous sampling of ligand and protein residue formation tautomeric states. C, improving the sampling of ligand-induced protein conformation changes. And over the past few years, we have been working on a number of novel methods to address those challenges. For example, we have implemented the ground canonical Monte Carlo, the GCMC method, to improve the sampling of water relaxation in the deeply buried binding pocket. And GCMC-enabled FEP dramatically improved the accuracy of French calculations, particularly for populations that displace water molecules in the binding pocket. We have also been working on general constant pH method and the protein conformation FEP. And those methods will dramatically improve our capacity to deal with targets with complex formation tautomeric states and flexible binding pocket. At the same time, we have also been working on absolute protein binding affinity FEP. And by rescoring the top compounds by inverse screen by ABFEP, the hit rate can be dramatically improved. With this, I'd like to acknowledge a large number of people who have contributed to the projects mentioned, and thank you all for your attention.
So it was a nice talk. So thank you. I think Dr. Linkle is still not available with us. So it would be great if you could write down your questions in the chat box and we'll clarify with the speaker and we will address that. I hope Nishanda is fine, right?
Yes, yes.
I think Linkle is still not available with us, I guess.
Right.
Okay.
I'm just checking once more.
I just checked.
Yeah,
It seems it's not there. So
yes.
maybe he has some inconvenience.
So,
I have typed his email in the chat box, and he will be very happy to answer any questions you email him. It's lingle.wang@schrodinger.com.
Great, Pratish. So, you can just chat your or type your chat in the next 5 to 10 minutes. So we'll go to the next speaker then. So our next speaker is Professor Cecilia Clementi. So Professor Clementi will be taking us to designing molecular models by machine learning and experimental data. So it's over to you, Professor Cecilia.
So you can try to share your screen. It should work. Yes.
Do you see my presentation?
Yes, yes.
Yes.
Thank you very much for the invitation. And yeah, I'll tell you something I've been working on in the last couple of years on designing minimalist molecular models using machine learning and experimental data. So to put things in context, I would like to start with what is our goal. So you all know that last summer AlphaFold was released and presented a very powerful tool to predict structure from sequences. It's basically, there was a lot of press and for instance, these are taken it from the press release and was said that it solved the protein folding problem. But what is that AlphaFold does? Of course, this is an impressive feat, it's a really impressive work. But if you think about it, it predicts one point in the landscape, one configuration in the configuration landscape of a protein system. And what we want is a way to characterize the full energy landscape. We could take the structure predicted from AlphaFold as the starting point, but we don't want to stop at one structure. We want to predict multiple, we want to predict ensemble in a metastable state and all the metastable states that are relevant for the protein function. And this is because the protein, in order to function, needs to dynamically explore this landscape. This is a movie taken from a recent paper, not from a group, showing how the protein changes configurations and jumps between different states. These circles here are metastable states, and the protein jumps between different states as it moves in the computational space. So this is our goal, our ultimate goal. Of course, and why we want to do this, of course, because when we have the full landscape, it's much easier to, you can understand the function of the system, then you can design enzyme, drugs, or you can understand diseases and so on. But of course, there is a big problem, that is the timescale problem. The fact that these fastest processes in a protein system are picosecond, like local reconfigurations, but the processes we are interested in are slower than microsecond, millisecond, or even slower than that. Especially if you look at protein aggregation, it's very slow, or even protein folding for decent sized protein. So clearly we cannot use brute force molecular dynamics with the highest resolution because there is no way to cover this range of timescales. So our solution, our approach is coarse graining. We want to find a physical model that is minimalist, contains only the minimal detail in order to reproduce the physical properties of the system. Of course, it's not the solution where this is possible is not clear, but we're working toward this goal. When we talk about coarse graining, there are different approaches. We can go top down or bottom up, or with alternative methods. For instance, and I'll talk about mostly about bottom up, but if I have time, I'll say something about top down as well. So bottom up means that our reference, what we want to reproduce, is the thermodynamics of a very accurate high resolution model, like we take as a reference all atom molecular dynamic simulation in explicit solvent. And we want to reproduce some properties, in our case, the thermodynamics, with a simple model. So we want to reproduce the thermodynamics, and this is reproducing the thermodynamics of a high resolution system using a lower resolution model is called the thermodynamic consistency. In order to reproduce the full thermodynamics, you need to match the free energy. And matching the free energy in the same, when you project in the same coordinates, and matching the free energy, if you require to match the free energy, this univocally identifies the effective potential for the minimalist model. The effective potential, that is actually a free energy, is given by the marginal probability of the high resolution model when you integrate out the degrees of freedom that bring you to the lower resolution model. The mapping from the atomistic representation, the highest resolution, to the coarse grain representation, we assume is given and is linear. For instance, we can take a slicing of the space. We can decimate degrees of freedom and keep only one atom per residue, for instance, or something like this. And we know the atomistic potential is given, and we want to find the effective coarse grain potential that reproduces the same thermodynamics. So in principle, there is a unique solution to this problem, but in practice, you cannot compute these integrals. And here is on the right is shown for the projection from 2 dimension to 1 dimension. If you have this 2-dimensional energy landscape here, and you say that you are interested just in the X dimension because Y is not interesting, then you have the effective potential you get is this curve on the bottom that is obtained by performing this integral. So these two models are thermodynamically consistent. But in order to do this, this has been done numerically, but in order to do something like this for a very dimensional system is not trivial. Fortunately, there is a lot of work by, for instance, Will Noyd and Greg Roth that showed that the same requirement of thermodynamic consistency that is shown here can be also satisfied variationally with the variational principle. So the same potential U that is defined by this thermodynamic consistency, by this marginal probability, is also the potential that minimizes dysfunctional when you can span the space of all, or the L2 space. So if this function U can span the whole L2, then the U which minimizes dysfunctional is the same as this U here. And so this is very important because it allows to use this idea variationally, and you can have ansatz function here with parameters and try to minimize the functional as a function of these parameters, and then you get a potential that gets closer among the family you are investigating, in the configurational, in the functional space you are investigating, you get the closest one to the real potential. The problem is it's very difficult to come up with ansatz function for this potential, because in this integral, even if the atomistic potential V didn't had only two-body interactions, in this integral you have the emergence of multi-body terms, because you renormalize away degrees of freedom. And so you need to come up with a functional form for U that has multi-body terms. And this is very difficult to come up with an analytical form that has not three bodies, four bodies, and so on. And we thought this is the perfect case to use machine learning, because we have a loss function. This can be thought as a loss function. And we need something here for U that has very large expressivity, because we want to cover a large functional space. So we put a neural network instead of U. So we take a data-driven approach. We start with all atom simulations, and we define this functional, we compute this functional on the data. We assume the data are Boltzmann distributed, and we put the neural network instead of U, and the data now are the parameters of the neural network, and we minimize this function as a function of the parameters. So we use this loss function for the neural network. And traditionally, a coarse-grained molecular model is done where you have the mapping, you go from the high resolution to the low resolution model, and then you have some function that part of it represents the local terms, like the steric constraints, and this is the easy part. And then part of it represents the non-local terms, the non-bonded interaction. And this is the difficult part. And this functional form is extremely easy, what I'm showing in this slide. And we have used it in the past, but this is not thermodynamically consistent. This satisfies some other properties, but doesn't match the thermodynamics of the atomistic model. So if we want a thermodynamically consistent model, we need multi-body terms. And this can be done, as I said, with the neural network. And why neural network? Because I already said that, because you can approximate, you can consider neural network as universal function approximator. So it allows, is a very expressive, and allows to, doesn't require to fit, to fix a functional form with parameters. You can express much larger functional space. And this is it too. There is the whole machinery of backpropagation and all the different minimizers to obtain, to minimize the loss function, to find the parameters of the network that minimizes the loss function. So we proposed, a couple of years ago, we proposed CGNet that is designed as follows. You have an input, the coordinate of the coarse-grained model. You go through a fissurization to have coordinates that are rototranslational invariant, that represent, basically they satisfy the symmetries of the system. And then you divide the energy into prior energy, that is the enforcement of some properties you want your system to have. For instance, the fact that there are bonds is a polymer, and the fact that you have excluded volume. Two atoms cannot occupy the same space. Or things like this, things that we know the system must satisfy. Energy requirement, we know the system must satisfy. And then everything else we don't know, in particular the multi-body terms, is captured by this free energy net. The two terms are summed, and this gives us the free energy, and then this effective energy, and then this is what enters this form for the minimization. And this works quite well. We showed in a proof of principle a couple of years ago, we showed for the small protein signaling, this protein is small, is 10 residues, but if you consider the reference simulation is several thousands of atoms, because include the water and all the atoms in the protein. And we reduced the dimensionality to 10 beads, so 30 degrees of freedom. So this is pretty aggressive coarse graining. And we showed that indeed this network architecture can reproduce the main feature of the free energy landscape of this protein. Here on panel A, you see the reference, the atom simulation, the free energy of the atom simulation. The main thing is that there are three minima: folded, unfolded, and misfolded. And indeed, our model reproduces the three minima, and the structures extracted from this minima, sampled from this minima, are very similar to the atom structures. Here in figure B, you see what we call the spline model. That is the best you can do using only two body potentials. If you have, if you use splines for, and you restrict the functional form of the potential to two-body interactions only, it's impossible to get a good match for the free energy. So really, this is the presence of multi-body interaction. Now, more recently, we have this model was a proof of principle. So we trained a model that is protein specific. It works only for this protein, but clearly this is not interesting, because we would like to train a model. We don't want to train a model for every protein. We would like a transferable model. So we designed an architecture that is transferable. So we borrowed some ideas from SNET, that is a neural network architecture that was proposed by Tachenko and Muller a few years ago, and we adapted it to our purpose. And an important thing of this network is that it learns the featurization. You input the distances, for instance, and then the featurization is learned. And the featurization is the features that you learn are auto-translational invariant. And then you go through the network and with the prior energy and so on. And in principle, this architecture is transferable. And we showed that it works for this protein, and actually it works better than CGNet. You have, if you measure the error that you make in the free energy, reproducing the free energy with CGNet and CGNet, and with measuring the error with a couple of different ways, by using the Kullback library divergence or the mean square error, the error in CGNet is smaller than the error in CGNet. So by enforcing some transferability, we also some sort of regularization. We also reduce the error. We make a smoother landscape. And this is what the results we obtain for the same protein. Again, we have three minima. That is the main feature of this landscape, and we have to extract structures from these three minima. They look very similar to the atom structures. And just to give you an idea, this is a simulation performed with this neural network potential. So this is the protein. This is the coarse-grained model of the protein that is unfolded, and now there is a collective transition, and it folds. And now if you wait, it's going to unfold and refold. So it behaves like it should. It's a very collective process, the folding and misfolding. And you see it in this different region of the free energy landscape. I mentioned several times that the importance of multi-body interaction. So we set to investigate this a little bit more, and we designed a neural network that is a multi-body expansion. So we designed a neural network that starts with two-body interactions only, that we know don't work, and then we add three bodies as a correction, and then we add four bodies, and so on. And we train all these different neural networks and compare. And indeed, we find that, so this is the error. In particular, if you look at for instance, the KL divergence, the two-body error is much larger with respect to CGNet. And we know it doesn't work. But also three-body, it reduces the error, but is not comparable to the accuracy of what the accuracy we would like. And four-body, the convergence is very slow. So we need up to 5 bodies to really reproduce something that is comparable to what you get with the neural network, where every term is included. And if we look at the landscape, this is the reference again, you see that the 5-body, the 2, 3, 4, 5-body potential is very similar to the whole atom. It's actually better than the CGNet itself. Again, probably this structure of the multi-body potential it's some sort of regularization in the model. And another thing we have been doing, we are trying to do this at different resolutions. And one particular application is a kind of hybrid model where we keep the resolution in the protein, but we constrain away the water. So this is an implicit solvation model that can be seen as a coarse graining of the water, renormalization of the water degrees of freedom. And so basically what we learn here is the solvation-free energy. We use as a prior energy the vacuum energy of the protein that is given by the force field. And then we learn the solvation-free energy by training on explicit water simulation. And the architecture is similar to the CGNet, is also in principle transferable. And this is what we get. This is for RNA peptide. So we get very good agreement, but for RNA peptide, if you also use a generalized Born model, the agreement is okay. But for the protein signaling, that is our test bed, the explicit solvent free energy that is given here on the left resembles very closely the free energy you get, our results at the second column here, and you get very similar free energy with our implicit solvation model. Instead, if you look at generalized Born implicit solvent model, there is one state is missing, and the folded state that is here on the right is very much unstable with respect to the unfolded state, while should be the reverse. So, and we get greater accuracy than with the state-of-the-art implicit solvent model, because we are trying to achieve thermodynamic consistency with an explicit solvent model. These are structures sampled from, and yeah, as a reference, the vacuum doesn't give you the folded structure. So in order to go from the vacuum that is used as a prior to these results, the network adds everything that the solvation free energy. And these are structures sampled from the different states. And you see that again, the reference structures are very similar to the structures sampled in our simulations. In the few minutes I've left, I would like to say something about the top-down. So eventually, we want to reproduce experimental data. We want to train on atomistic potential, but the ultimate goal is to have models that can be predictive in terms of real world. And that also the atomistic model, they are, even if they are high resolution, they are not completely error-free. They are not guaranteed to reproduce the experimental data. So we want to make sure that we want to anchor our model to the experimental data. And so right now we're pursuing this project as in parallel, but eventually we'd like to merge the two lines. So the idea is that instead of first making a model and then comparing to the experimental data, that is the direct route, we want to take the inverse, and we want to start with experimental data and make sure that our model matches the experimental data. And we have been working on this for many years, but we have published also like 15 years ago on this stuff, but now we have a fresh take on the problem, and we are using some maximum likelihood framework to do this. So the idea is to have a likelihood, to define a likelihood that is a function of the agreement that quantifies the agreement between the experimental data and our predictions, and is a function of the parameters in the model. The model can be a neural network or can be a model with some functional form. But if we manage to write a likelihood as a function, a specific function of the parameters, then we can maximize this likelihood and find the parameters that give us the optimal model. And also, as a bonus, we also have a likelihood for this model. We know how well this model works. And so in more in detail, we start with the guess for the parameters. So a guess for the zeroth order Hamiltonian. We have a set of experimental measurement uncertainty, and we simulate the system. So we obtain an equilibrium distribution. From the equilibrium distribution, we can predict the observables, the corresponding observables for which we have the experimental measurements, and we write the model likelihood, and then we make it explicit in the parameters by using a reweighting trick. Basically, we express, by using a reweighting trick, we can write a stationary distribution as a function of delta epsilon, and this goes inside the likelihood, and so we make the likelihood as a function of delta epsilon, then we pick the delta epsilon that maximizes the likelihood, and we iterate. We tried first this on some toy model on simulated data, the simulated experimental data. These are simulated threat data, and you see that we can match the simulated data very well. So this is a minimalist model trained to reproduce experimental data that instead of real experimental data are obtained from an atomistic simulation. And it works very well. We can match the reference curve very well. And more recently, we are doing it with real experimental data. We can do it with NMR, and we can get a good agreement between the NMR J coupling and of the model and of measured in experiment is for ubiquitin. And that agreement is comparable to the agreement of all atom simulations. Or more interestingly, we can use mutational data. We can use, using for perturbation theory, we can simulate mutations. And we consider only a conservative mutation that go from large to small. So we consider basically cutting bonds. And we can reproduce the delta G of mutation. And as a first application, we try to see with this approach how far we can push a two-body only potential. And we use it for two proteins, ubiquitin and protein G. And ubiquitin seems to work. Ubiquitin, if you use a bunch of delta G's from mutation, you optimize the model. This, in orange here, you have the results. You can have a decent agreement between the experimental and the calculated delta G's. And this is using only a two-body interaction. Two-body interaction, functional form that includes only two-body interaction. But for protein G, it fails. The optimized model cannot be optimized more. So the likelihood is pretty low for the optimal model. It cannot match the experimental data. And in particular, you cannot match the experimental data for residues that are solvent exposed. If you mutate residues that are solvent exposed, you cannot, with the two-body potential only, reproduce the delta G's. And this is indicative because it means that in order to produce the water environment, you need multi-body terms, and not too surprising. And indeed, when we introduce a multi-body term, we can correct the model and make it in agreement with experimental data. So this was done with functional forms, but eventually we want to merge it with the neural network approach. So with this, I would like to thank all the people who have done the work. In particular, I've talked about the work of Nick and Irina, and also my previous postdoc, Chang. And now I have new people. Felix is working on this problem, and Andrea. And also I would like to thank the funding sources and all of you for your attention. Thank you.
Thank you, Professor Cecilia, for a wonderful session. So the session is open for discussion now. We have quite a bit of questions, so we'll take up one by one. So the people here can unmute themselves, and if you can ask your questions, that would be great. So maybe I can just initiate that. So Jagannath, I saw some questions from your end.
Yeah, I think my question was that for the part where you talked about the CGNet and SHNet, so wanted to check like the point of doing the coarse grain simulation to make sure that we don't have to wait for atomistic simulation to be over, but you have the underlying input for your neural net is atomistic simulation data. So what I wanted to know is that how much data do you think that is actually necessary to train so that we can actually get a good coarse grain model?
Yeah, so this is why we want to do it transferable. We want to do something that you train on data for some proteins, but then you use it for other proteins that you cannot simulate by your atom. And we are working on this right now. We have encouraging results, but it's not finished yet. So we are also working on many aspects, architecture, the loss function. We are trying to optimize every single aspect of this project in order to achieve our goal. Our hope is that we will not need too much data, at least, data that we can handle, and for a limited number of proteins.
So we have another question from Professor Peter Borges. So Peter, you are there?
Yeah. So can you see me or hear me?
Yeah.
Yes.
Yeah. Hello. Hi. Hi, Cecilia. A nice presentation. Thanks. I was wondering, so if you have a coarse grain network, or it's a CGNet, is it possible to interpret this in physical terms? So can you actually have some sort of a maybe multi-body interaction, and can you interpret this in a sense?
Yeah, this is what we would like. This is why we did the work on the multi-body terms. We want to weight a different multi-body. That was a little bit surprising for us that we needed such a higher correction, because that is kind of bad news, because it's very difficult to fit five body potentials. But I have to say that this was the resolution of this model was carbon alpha only. Now we are using different resolutions too, so maybe different resolution don't require to go to such a high body order. If we have to fit 3-4 body, we could try to do it analytically.
Is it possible to constrain the number of the multi-bodiness?
Yeah, we can do it in the network. This is what we did in this multi-body expansion. Okay. And this is what we saw, that if you use 3 body only, doesn't work. If you use 3 body, 4 body, it doesn't work very well. You need to use 5 bodies.
Okay. Well, thanks for clarification. Thanks.
Yeah, so we still have time for a couple of more questions. So Professor Strabon, you are there?
Yes. Yeah. So basically, I wanted to know that in the figure that you have shown, there is a gap between the surface of the protein and where your implicit solvent range starts. So when you do this dual resolution do you do any dual resolution for the solvent, or all the solvent molecules are implicit here?
All the solvent molecules are implicit.
So what happens if you have open clefts where water molecules can come in?
It's implicit.
This is why it is implicit.
Yeah, this is why you need higher order interactions, because somehow you need to reconstruct the effect of water from the neighboring atoms.
Okay. Okay, and what about, dynamics has no role to play when you are constructing the CG nets, because what I was trying to think is some of the water molecules near the surface of the protein will be a little different from the ones which are very far from the surface. So do you add some higher body interaction to those water?
So right now we let the network learn And then we haven't looked at cases where we have structural water. This is an interesting problem to look at. Right now, we are trying to make it work in general. But also about the dynamics, when enforcing thermodynamic consistency doesn't say anything about the dynamics. We don't expect the dynamics to match. We are working on other techniques to try to recover the dynamics, but just doing thermodynamic consistency doesn't preserve the dynamics.
Yes. Thank you.
Maybe we can take one more question, maybe one last question. So I see one question from Sapna. Sapna Sarpriya, if you are there, if you could ask your question.
Yeah. Hi. Really nice talk, Cecilia. I had a quick question. One was I was just looking for the details of how you're making your coarse-grained models transferable. But I think I was also thinking about in making them transferable, do you decide a priori what the bead size should be? And do you expect that bead size to always be same for different proteins in different conditions?
So more than the bead size, what's important is the bead resolution, because the size is determined by the excluded volume, and this is something we fit on the data. We fit on a large set of data, so it's not just for one protein, it's for an average protein. But the resolution, what is the optimal resolution? This is an open question. We are trying to investigate that, but right now we are using different resolutions. It's not clear what is the resolution, if there is a resolution where we can have a decently transferable coarse-grained model.
Okay. And would these be transferable across solution conditions as well?
So right now we are working on transferability in sequence space. We work at a fixed thermodynamic point, fixed temperature and solution and so on. So all our training data are obtained at the same condition, the same force field, same temperature, and same in solution. But if this works, we would like to also possibly expand it to transferability in temperature, across temperature and so on.
Thank you.
Thanks, Sapna. So we still have got a couple of more questions in here, but we have hit the time, Cecilia. Thank you once again for a wonderful session. Thank you.
I'm happy to answer questions. 1 second. I'm happy to answer questions. People send me an email. I'll put my email in the chat.
Yeah, that would be great. Yeah. Thank you.
Thank you.
Okay, so we have already hit the time now. So we'll go to our next speaker for the session. We have Professor Omar Walson. So he'll be taking us through understanding long time scale phenomena in chemical and soft matter systems with variationally enhanced sampling. So over to you, Professor Walson.
Thank you. Thank you for the introduction. Let me see. Okay, so I can share.
You can share your screen. Yeah, it's visible now.
Okay. Okay, I actually changed the title slightly because I was going to talk about kind of 2 different projects today, or 2 different works. The first is kind of related to the initial title, which is variational sampling. This is a bit of work that we are just finishing now and is ready for submission on kind of using wavelet-based bias potential. And the second piece of work I'm going to talk about is a method which we call multiscale reweighted Stokastic embedding. It hits on a theme that has been commonly discussed in this meeting, which is using machine learning for finding collective variable. So let me start with the first project, which is this wavelet-based bias potentials. So variational enhanced sampling is a collective variable-based enhanced sampling method, which I introduced a few years ago. It's a method based on a variational principle, where you have this kind of functional of the bias potential. And by minimizing this functional, you kind of construct effective bias potential in some given CV space. So you minimize the functional, and the bias that minimizes this functional is related to this so-called, related to the free surface. So in practice, how you do this minimization is that you introduce a linear expansion for the bias potential. So then now it's gonna be some expansion coefficients. So you have some kind of convex optimization problem in some high dimensional space of this alpha coefficients. So in this way, you can kind of minimize this functional and kind of obtain a bias that enhances the sampling. So this method offers very interesting possibilities in the form of the bias potential and the sampling that can be achieved. So this method is completely general and can be applied to a wide range of problems. And kind of for further information, you can look at this review paper chapter from last year. And it's available in Bloom 2. So what we are focusing on here is this kind of this bias potential, how we represent this bias potential in some set of linear basis functions. To say we have this basis set expansion in some basis functions. In this way, we can kind of represent any general fringe surface. And like in 2 dimension, you can just use a tensor product of 1-dimensional basis functions. So far, we have been using kind of delocalized and orthogonal basis functions. For example, this could be like plane waves or Fourier series for periodic series, or Chebyshev Lagrange polynomials for like bound series or non-periodic series. So, but sometimes the behavior of this kind of delocalized basis function is not always robust. And what can happen is that because they're delocalized, that you might be changing the bias in the part of CV space where your walker or simulation is not currently exploring. So it can be a bit not so robust. So this project was kind of initiated by this idea, might localized basis function perform better? So this is what we want to understand in this project, in this work. And when you think about localized basis functions, the first thing you might think of would be Gaussians or cubic splines, which are kind of localized basis functions. When I talk about Gaussians, this should be clearly distinct from how Gaussians are used in aerodynamics. When I talk about Gaussian basis set here, I'm talking about that you have fixed Gaussian on fixed location in CV space that cover the whole space. And when you optimize the bias potential, you optimize the coefficient in front of the Gaussians. So it's not like aerodynamics where you depart the Gaussians. The Gaussians are always fixed. But as I say, the first thing that might come to mind for localized basis function would be Gaussians or cubic splines. In fact, Gaussians have been used as basis function for Bayesian and sampling, but have not really been compared to other basis functions. However, one issue with the Gaussian and splines is that they don't perform, are not orthogonal basis functions. So what we start to look at are wavelets. Wavelets, for example, have been used for coarse-grained simulations, or are used in like the DFT codes, like the big DFT codes is based on wavelets. So these wavelets are the small wave-like basis function fulfilling this following refinement equation given here, where this phi is the father wavelet and the psi is the mother wavelet. And these functions, they form an orthogonal basis set. What is also interesting about these wavelets is they have this kind of multi-resolution property given by this equation here. So you start by one layer of kind of father wavelets given by the first term, and then you can introduce another level of wavelets on a smaller scale to kind of increase the accuracy, even just locally in a part of the space. But so far, we're only using kind of a single level of father wavelets for our bias potential of some given type of scale. So then is the question of which kind of type of wavelet we should use. We quickly observed that it's better to use so-called least asymmetric wavelets, which we call simlets for simplicity. They are not fully symmetric, but as you can see in these following figures here, they are close to being symmetric. So then there are different types of the wavelets, where this sim and the number determines how many coefficients are used in this recursion or refinement equation. This also number determines the number of vanishing moments. It's basically that a simlet of order 10 can accurately represent a polynomial up to order 10. And so forth for simlet of 12, you can accurately represent a polynomial order 12. So as you increase the kind of number coefficient, you get like a more smoother wavelets. We observed in our simulation that if you're above a certain value, like simlet 8 or 10, you get pretty good results. So we found that using like simlet of order 8 or 10 gave good result. So in all results are obtained using either simlet 8 or simlet 10. And to say, we use this asymmetric wavelets, and I just found out that this is actually the same as I used in the big DFT wavelet-based DFT code. Now, of course, there's one particular problem, or a minor problem, I would say, is that these wavelets, they don't have any analytical formula. So what we do is that we generate them a grid via iterative scheme. So, but this is only done in the beginning of the simulation. You just generate a large grid with a fine number of grid points in the beginning of the simulation, and then you just use that as a lookup table during the simulation. All this work was done by my PhD student, Benjamin Pampel, that did all the heavy work of understanding and implementing all of this numerical algorithm for generating the wavelets. Of course, it should be noted that like here, I only show two wavelets in this figure here, in the above figure, while of course, in reality, to cover the whole CV space, we have like a full number of wavelets that cover the full space, as shown here in the lower figure. In this way, we have a complete basis set for our bias potential. So the first thing that we did was just to look at model systems. So we look at here just like a single particle moving in a one-dimensional potential described by a kind of Langevin thermostat. So on the left side, I have the Lagrange polynomials, which have been, for example, using so far as basis function. While on the right side, I have this new type of wavelets basis sets. And as you will see when I start to run the simulation, is that the wavelets are considerably more stable in time, while the Lagrange polynomials fluctuate much more during the simulation. You can see that the wavelets are basically stable, while the Lagrange polynomials are quite fluctuating. You can also see this much clearer in this figure here. Here, I'm showing the kind of a time series of an error metric that just calculates the difference of the fares obtained from the simulation to a reference fares, which is just the underlying potential. And we average over 20 independent runs. So the dotted line is just the average, while the shaded area is the standard deviation or standard error of the mean. And you can clearly see that the wavelets perform the best. They show much less fluctuation in the average, and also much less fluctuation between runs. And while the Lagrange polynomials show much worse result. And otherwise, the Gaussians and the splines also perform reasonably well, but are not as good as the wavelets. We can also see this just by looking at, because this is average over 20 independent runs, to give kind of an sample average of the result. But we can see here, if you just look at the result for the individual runs, that really clearly the wavelets are considerably better, gives considerably better results if you look at the just the individual runs. And the same, as you see here, that there's a lot of fluctuation in the Lagrange polynomials. And the same is seen if you just look at the frequency difference between the two metastable states, is that the wavelets fluctuate much less. While I say that here that the Gaussian and spline work fine, we observed for the other system that will come on the following that they were not always robust. So sometimes the Gaussian or the spline did not work so well, So I will not really talk about them some more because our experience that they are not really recommended. So in the following, I will just focus on the wavelets and the Lagrange polynomials. So the next case is just a two-dimensional system, the Wolff-Quapp potential, where we're using a tensor product of two one-dimensional wavelets. So we're biasing both the X and Y direction. And here we see the same, and here I just show the time series of the Freeney difference between the A state and the B state, which is separated by the this line, the epsilon equal to 0 line here. And you can clearly see that the wavelets show much more robust convergence behavior compared to the Lagrange polynomials. So there's, as you can see that here, there are basically two things which you can see, that within each individual run, the fluctuations are much less with the wavelets, and also importantly, the fluctuation, the differences between independent runs are much smaller. So there are two benefits to using the wavelets, which we can observe. And then we also looked at the rotated Wolff-Quapp potential, which has been kind of proposed as a prototypical example of biasing a suboptimal collective variable. Here, we're only biasing the kind of X coordinate. So we're missing this, the epsilon coordinate that is kind of missing in the biasing. So here we can see that the results are not as good for the other system, but this is due to the fact that we don't really have a good collective variable here. Still, if you look at the average over kind of 20 independent runs, we get decent agreement, convergence to the reference for the wavelets, while the Lagrange polynomials fluctuate a bit more. Although I should note here that the fluctuations are a bit different here, because we noticed while doing the simulations that the so-called average stochastic gradient descent algorithm, which we use normally for variational Handel sampling, was not performing so well for this system. So here we started to use the atom optimizer, which is quite well known for the field of machine learning. However, interestingly, the atom worked worse for the other system. So this is not really clear to us what is always the best optimizer. So, but as I say, it worked fine here, atom, but not so well for the other system. But this is definitely something which I think is worth looking into better, how maybe to improve the optimization process. So finally, we looked at a more kind of realistic system. So here we looked at the association of calcium carbonate in water. So this is all based on a kind of previous study, which was published a few years ago. This is work by Julian Gale and Paolo Retteri, where they were looking at the association process. So we obtained the force field from Paolo Retteri, and also Paolo also gave us some reference result, which I will show later here. So this is kind of so they did quite extensive sampling using meta-dynamics in this paper. So here they use two collective variables, which are kind of another collective variable for the system, which is just the distance between the carbon and the calcium, and the coordination number of the calcium with the water, with the oxygens of the waters, which tells us how basically the solvation of the systems. And we, as stated, we use well-tempered meta-dynamics, or the well-tempered variant of variational sampling with a bias factor of 5. And we use multiple Walker simulation for all setups using 25 Walkers. And for each biasing setup, we run 3 independent simulations, because as we saw before, also the difference between independent runs was quite striking for the model systems. So this is the kind of fringe surface that we obtain. So, and here it's necessary to use both collective variables because they are quite coupled, the solvation and the distance. So this is the fringe surface that we get. from the simulations. But to kind of compare the result better, we just look at the projection on the distance. So here, this is just the different simulations from the different biasing setups. And we all line them that the minimum is at 0 here. As you can see here, for this part here, where we have the associated state, they all agree well. While for the kind of dissociated state, there are some differences between the results. Well, also all method capture well this kind of small barrier at around 3 angstrom. So we should note that this is not a real barrier because we have integrated out the solvent degree freedom. You will need to really have the solvent, the other two-dimensional fringe surface to understand the best properly. So, but the thing is that even if you look at the reference result, which we obtained from this previous work, they all also differ quite a bit, similarly for the dissociated state. So we can see here there are some differences here in the top figure, and then we look. If you look directly on the figure on the left side, for the different methods, the different biasing setups, we can see that the wavelets, all these different simulations give kind of pretty similar profiles. While there's quite some difference for the Chebyshev polynomials. While also the meta-dynamics is in better agreement with each other, similar like the wavelets. So here we can already see one conclusion that we saw before is that the wavelets, that the difference between independent runs is much more similar. Of course, we can also, this is the fringe surface obtained directly from the bias potential. This I think is the fair comparison here because we are looking at the form of the bias potential. While in reality, we can also use, get the fringe surface from reweighting. And this is the fringe surface from reweighting here on the right side. And you can see that actually the reweighting seems to kind of correct a lot for the difference between the independent runs. But then we are missing a bit the time information of the simulation. As we saw before, there were much more fluctuations between the in the delocalized basis function. So to kind of look at this, what we did do is that we calculate the fringe difference between the associated state determined by the barrier around 4 angstrom and the dissociated state, which is above 4 angstrom. So this is how we define these kind of 2 different states. So we calculate the fringe difference for the different method. Let me see. So this is what we show here. So here we can clearly see that the wavelets are more stable than both the Chebyshev polynomials, and they're really much more stable than the Chebyshev polynomials, which are really quite fluctuating a lot. And they're even more stable than the meta-dynamic simulations. And this is also observed here in the figure on the bottom, where we basically calculate the average over the last nanosecond of each walker. So this is like the last 1/3 of the simulation. And you can see that the standard deviation is much smaller for the wavelets, and they're all kind of in similar agreement. And you can see that also the reference are a bit different. So but all the results are within like 1 kilojoule per mole. And then we can also do the same by doing reweighting. And then we also see that the wavelets are kind of all start to agree better with each other. And interestingly, like the meta-dynamic simulation, they start to go a bit down and become more closer to the wavelet simulation. But as I say, we don't really have the exact reference value for the system. So this draws me to the conclusion of this first part. So as I say, the wavelets exhibit much more robust convergence behavior than the delocalized basis function. There are far smaller fluctuations within individual runs. For example, this would be important for kind of reweighting, which kind of makes, there's an implicit assumption that we have a quasi-stationary bias. So if the bias is fluctuating less, the rating should in general be kind of expected to be better. Though we don't really see striking evidence of this in the previous system. And also there is a smaller difference between independent runs. As I said, I don't show the result, but we found that the Gaussian and spline, they perform worse than the wavelets in general, and they are also are not robust. So the main conclusion is that we recommend wavelets, or in fact simplets, as basis function for VAS simulations. And we just merge our implementation into the master branch of Plumed. So this will be available in Plumed version 2.8 as action there. And actually, we also implemented periodic version of the wavelets, but I don't show results about that. But that's also possible. I mentioned that it's also possible to use the periodic version. So then, of course, maybe a future work would be interesting is to go back to this idea of multi-resonant bias potentials by looking at the full equation, where we can maybe increase the resolution on the fly during the simulation. And as I say, this is work that will be submitted in the next weeks or so, soon. So this then brings me to the second work I'm going to talk about, which is a common thing which has been discussed heavily in this conference, is the issues of the collective variables. As we all know, the performance of collective variable-based enhanced sampling method depends heavily on the quality of the chosen collective variables. Meaning effective collective variables, they should, of course, discriminate between the relevant metastable state, include most or if not all of the slow degrees of freedom, and we need them to be few in number. And as you know, typically these kind of CVs are constructed manually by using physical and chemical intuition, often using a trial and error. You try a set of collective variables, you see some issues, you try another set, and then you find after many maybe different tries, the set of collective variable works, and you get your paper published. But of course, behind this is a lot of trial and error. So there's a lot of interest in the field of using kind of, to say, it can be far from trivial to find a set of collective variables that quantify all the essential characteristic of the system. So there's a lot of interest in the field to use machine learning to automatically construct or find these collective variables. So you have some kind of machine learning algorithm or a dimensional reduction algorithm that looks at your system and finds these collective variables. So how this kind of machine learning method work? Generally, they work by that you introduce or define some high dimensional feature space. And this could be like dimension 10 to 1,000 of features or descriptors. This could be like distances, like pairwise distances, dihedral angles, backbone atom positions, coordinate numbers, symmetry functions, and so forth. And then you define some neural network embedding that depends on some parameters that takes your feature space and maps it into a low-dimensional CV or Latin space, which is on the dimension 1 to 3 CVs, and this is then your kind of CV space. So normally you do this by introduce some kind of training data, and then you train the neural network by minimizing a loss function. In the method that I'm going to talk about is based on the idea of stochastic neighboring embedding. In this stochastic neighboring embedding methods, you define in the feature space pairwise probability distribution in the feature space, and you do the same in the Latin space. So in the feature space, you have some kind of defined pairwise distribution, while in the Latin space, you have also this pairwise distribution, but they normally depend on some parameters as defined by the theta. And then once you have defined these two different pairwise probability distribution, you minimize the difference by using the Kullback-Leibler divergence. So you minimize this. The Kullback-Leibler divergence is the loss function for the minimization. Okay, so to say this is just, so yeah, as I say, we define this probability just based on pairwise distances in the feature space in the lattice space. In the so-called T-distributed stochastic neighborhood embedding, or TSNE, the feature space is a Gaussian, while in the lattice space you use a T-student distribution. So in this way, by using this different distribution, especially using the T-distribution in lattice space, which is more has a fatter tail, you ensure that similar points are grouped together and dissimilar data points are separated in the lattice space. One issue with TSNE is that you need to define basically the bandwidth of the Gaussians in the feature space. This is done by introducing a parameter called perplexity, and which you then you optimize the bandwidth of the Gaussians to fit this perplexity. So you have, and the result depends heavily on this kind of value of the perplexity. So, but we use the similar ideas of a Gaussian feature space and a T-distribution from the other space, but we kind of build on top of that in various ways. This method that we call multiscale related stochastic embedding. This is work done by Jakub Rydzyński in Poland. So the first thing that we do while working with these methods is that we use a neural network as for parametric embedding. Often the TSNE, for example, is just it's not a non-parametric method, so you don't have a neural network. And of course, having a neural network is essential if you want to use the collective variables for biasing, because you need to get the derivative of the CVs. And the second thing, which kind of avoids the issue of this perplexity, instead of using a one layer of Gaussians for the feature space, we use a Gaussian mixture. So we use a Gaussian mixture where it takes a sum of the different values of the perplexity. So we get away with of having to set the perplexity parameter because we use just a sum over multiple values. So in this way, there is no perplexity parameter that the user needs to set. And thus, the results will not depend on this parameter. We just use a set of them. And this is also got in this way, we obtain a multi-scale representation, and which allows us to have a better description of complex 3D landscapes. And as I say, it's a parameter-free method. But secondly, which is also important in relation to enhanced sampling, we would want to use the methods for enhanced sampling simulations. In this case, if you're using machine learning method for that, you often do iterative things where you bias, and then from the bias simulation data, you learn a new machine learning collective variable. And you need to do this normally because on bias simulation, you don't observe transitions. But of course, this means that we need to train from bias simulation data, and this we need to account for during the training. So what we found after some trying different things, this is the procedure we found to work well for us. So we incorporate the reweighting procedure in two ways. First, we use a landmark selection to select from the bias sampling landmarks that are more closely distributed according to the equilibrium distribution. And I will talk about that in the next slide. Secondly, so the training data should be more closer to the equilibrium distribution rather than the bias sampling. But we can control this via parameter, as I will show. But we also incorporate reweighting in the training by using this reweighted Gaussian given by this equation here at the bottom. So we also incorporate the weights into the training. And also say that we implemented everything into.
Professor Walson, if you could conclude in another 2 to 3 minutes so that we can take up some discussions.
Okay. We did this via prompt implementation, and this is available. It's not publicly available, but it's available in the Synology dataset with the method. And we're working on a more general implementation. And for further information, you can see this paper here. Okay. Okay. So as I say, we need to use bias sampling to take the weights into account for selecting the landmarks. We use kind of weighted random sampling. And we basically use which select weight according to select some landmark according to the weights. But what we do here is that we rescale the weights in this following way. This is called weight tempered random sampling. This is similar to the spirit of well-tempered farthest point sampling developed by Michele Ceriotti and Gareth Tribello in relation to the sketch map. So we get this feature distribution here. So where we have this alpha parameter that we can control, that either we get if we have alpha 1, we get should get the equilibrium distribution. For alpha infinite, we should get the bias distribution sampling of the landmarks. So this is just an example of the landmarks. Here I have a reference. And we select 4,000 landmarks of an initial set of 100,000. So this is the reference data. We use metadynamics. The sampling is given here. And based on this alpha parameter, we can see how the distribution of the landmark changes. As we go higher alpha, we get closer to the bias simulation. While if we use small alpha, we get basically the equilibrium distribution. And we found that it was optimal to use alpha 2. Okay, skip this. So the first test case is alanine dipeptide, and here we train on here first I show MRS embedding trained on bias data, just parallel tempering, so it should capture well the equilibrium states. And here I show embedding trained on bias simulation data with different biasing strength. So they're just different metadynamic simulations. So we have different embeddings, but they all look rather similar. And clustering shows that the states are correctly mapped and separated. But we also looked at one thing we looked at is the frequency difference between some of the states. Because this frequency difference defined here, this equation is only valid if the collective variable correctly separate the different states. So it's a good test to see if the embedding do this properly. As you can see, all the results are basically on the reference line here for different results. So maybe I just have 2 slides. So to say, then we looked at the alanine peptide, where we're biasing 3 collective variables. And if you look at the the fringe surface here, we can identify 10 different metastable states if you look at as a function of the different phi angles. Here I just show so-called conditional fringe surfaces, which we use to visualize this 3-dimensional surface in 2 dimensions. And let me see. Okay, so basically the bottom line is here is that many of the states are quite high in free energy. So if we train on unbiased simulation data, which is parallel tempering, which is fully converged for the lower regions, we only capture 3 of the most populated states. So we can only capture all of the states if we train on the enhanced sampling simulated data and use the reweighting. So this shows that it's really often essential to get embeddings that capture all the states to use enhanced sampling simulation data. Okay, so as I say, this is just conclusion of this part. As I say, gives parametric embedding via neural network. We have a multi-scale representation with this no perplexity as in TSNE, and the method supports learning from biased data. And we are currently working on using the methods on more complex system and biasing using using the neural network embeddings. This is first example of this, where you use bias this on ALA3. Finally, I would just to maybe mention that this is really my last talk as a group leader at the Max Planck Institute, as I'm starting as a assistant professor at the University of North Texas in Department of Chemistry now, just next month. And I can tell that I have opening for a postdoc early next year, and our official announcement and advertisement will come out after the new year. But if you're interested in a postdoc position or applying, you can also get in touch if interested, and I can keep you updated on the official announcement. And as I say, my group will be working on method development and application to protein-protein interaction, photoactive system, and molecular crystals. And with that, I'd like to thank you for your attention.
Thank you, Professor Wilson. It was a great talk. So we have time for a couple of quick questions. So we are already on to our break time, but I guess we can continue with our question and answer session, right? Is that okay, Nishan? Yep. So okay. So we'll take up our questions. So we have Jayshrita Devnath. So if you could quickly, Jayshrita, you are there?
Yes.
Yeah.
I wanted to ask, so how do you choose which wavelets to use, and do you still have to choose the minima and the maxima for the wavelets, like in Legendre or Chebyshev?
Yeah, you have to do that. Meaning we observed above a certain value that they kind of worked that we did, of course, like initially just trial and error. So we initially tested, I think, 8 or 10, or Benjamin tested. And let me see here, I have the slide. So above, if you use 4, the results are not good, but if we use above 6, 8, or 10, we get different convergence. We get good convergence of the results, but still we need to choose the we need to choose the boundary. That's true. We need to still choose the boundary, but this can be just in the same way. But we don't observe any boundary effects in general.
Okay, so the procedure is same like in using Legendre or Chebyshev.
Yeah, but there's
Thank you.
Thank you, Jessica. So Diman, you are there? Diman Ray.
My question is that as an user, like how would I understand that in which situation a metadynamics will work better, and in which situation the VS with the wavelet will work better? Like how will I choose the method to use?
That's a good question. I think I don't really see that. I don't think I can really answer that. That's meaning it's meaning both methods should work reasonably fine if you have good collective variables. Neither of them, neither of the things will save you if you have bad collective variables. So I believe in most cases they should behave rather similarly. So there might be small differences, but that will depend maybe on the system slightly. So I cannot really, I don't think I can really give you a clear answer about that.
Okay, thank you.
Thank you. Peter has a quick question. So Peter, you are there?
Yeah, I'm here. So thanks, Omar. Very nice presentation. Good to see you. I had a very simple question, actually. I was struck by the fact that the wavelengths work much better than Gaussians, and I was wondering why that actually is. I mean, what is the origin of that?
We are not really sure. I mean, there is one thing maybe I did not, there's one thing which we looked at is that the Gaussians actually have one parameter that that is basically, okay, like here for this system, the first system, the Gaussian actually work reasonably well, but for other systems, they did not work so well. There's one, I don't have it here. Okay, there's one parameter which we actually observed affected the Gaussian results a bit, is that when you determine the Gaussians, you set up the Gaussian basis set, you just set the number of basis function in the range. And then you just put them uniformly in the range. But then there's another parameter which is kind of can be adjustable, which is the sigma of each Gaussian. So Benjamin found out that actually if you use the default value that from the paper that used it, that gives worse result. So you can see here on the left result using the sigma with different values. So here is relative to the distance between each Gaussian. So it might be that the Gaussians can be optimized by optimizing the sigma for each case. That might be, or it could be that fundamentally this is related to the fact that the Gaussians are not orthogonal basis functions. So that might affect the optimization in ways which we don't really understand yet. We did not really put much effort into understanding at least at this point. We kind of we were initially focused on using the wavelets, so the Gaussian was just a comparison. So we didn't really maybe kind of really go deeply into testing them for each case. But I have to admit I don't really know why they work.
It's clear. I did some more research. Okay, thank you.
Thank you, Peter. So I guess we will conclude this session. Now we have one more question. So Omar, if you could just answer that questions in the chat box, it would be great. And if you could just give your human ID so that any further questions can be communicated to you. So thank you. So let us thank the speaker for a wonderful session. So thank you, Omar. So we'll go on to our next speaker for the day. We have already done with our break time. So we'll just continue with the session and finish off the session. So we have Harish Vasisht here. So he'll be talking about rare events in RNA conformational dynamics and ligand recognition. So it's over to you, Harish.
Thank you, Padmesh. Can you hear me?
Yeah. Okay. Please share your screen.
Let me try to. How about now? Can you see my screen?
Yes, it is.
You can?
Yeah.
All right. I'm going to put it in
Let's
the
put it in the full
presentation.
screen.
Yeah, sometimes one loses the. How about now? Can you see it in the full screen?
Yeah, it's fine. You can continue.
Okay, great. Thank you so much. So how much time I have? About 25 minutes?
Yeah, you have 25 minutes. So it is 9:22 here. So you'll have another 25 minutes plus we can take 5 minutes question session.
Great.
So that would be great. Yeah.
Okay, thank you.
Yeah.
Well, thank you everyone for coming to this final talk in the entire meeting. In fact, not only in the session. A few minutes back, Nishant was sort of panicking if I'm going to show up, and I was busy with my weekend job of making breakfast for my family on Saturday morning. So I'm grateful for all of you for coming to the meeting. So today I'm gonna speak a little bit about one of the biomolecules that we haven't heard a lot about, at least in this meeting so far. Particularly, I'll be showing you some of our simulation work related to RNA molecules. So before I begin, I wanna say a few words as to why choose RNA. Why RNA has been so less studied compared to proteins and many other biomolecules, and particularly what some of the exciting questions are in the RNA field. So based on my reading, I think one of the key challenges in studying nucleic acids in general have been a lack of experimental structures, particularly for RNA, because RNA is so different from its other cousin, which is DNA, about which we know very stable structures for a long time. RNA is single-stranded, it could be double-stranded. It's conformationally very flexible, and it presents unique challenges for practitioners of molecular simulations that try to optimize these interatomic potentials, force fields for RNA molecules. So if you follow the field, RNA force fields have been fairly challenging. Lots of modifications have been made to them, way more than I think in proteins, and they continue to be modified even until very recently. So this likely has, I think, demotivated a lot of people from pursuing large-scale simulation studies in RNA. But some new developments in the force fields very recently, I think, where they have been tested on fairly long time scale simulations, as well as different kind of structures, like, RNA can come, as I said, in many flavors structurally. And it's been tested and established that force fields currently, especially the AMBER family of force fields that we have used in our entire work, I think are doing a reasonably good job of capturing this.
Harish, are you changing the slides?
Yeah, that's what I was going
No,
to ask.
I haven't changed any slides yet. No.
All right. Yeah,
Yeah.
Sorry.
Right. Yeah. So it has essentially, the force fields currently, in my view, are reasonably good, and they are being used quite a bit. And I'll show you all of our work. I was saying is conducted with the AMBER force field, and for the MD software, our primary tools are NAMD as well as AMBER. No good rationale other than our ability to modify these codes and our experience in working with these codes for a long time. So there's no particular preference other than that. So in probing these questions of RNA conformational dynamics, where should one start? One is always looking for, as we saw in other talks, good model systems that are somehow well characterized, previously studied, where comparisons could be made. One such system that we have started to work on is this small RNA molecule known as transactivation response element RNA, or TAR RNA. It's a fairly small RNA molecule, comes from the HIV-1 virus. So if you look at the genome of the HIV-1, which is roughly about 10,000 nucleotides long, and if you zoom into one end of this genome, I think the 5' end of the genome has this very small hairpin-like structure. This is called the TAR RNA molecule, and I'm showing you its sequence as well as its structures as it is experimentally characterized. So this TAR RNA molecule is known to contain basically two short helices, helix 1 down here and helix 2, which are formed by fairly stable complementary base pairs. And these two helices are connected by this flexible bulge motif shown in red in the structure, and a small loop motif that's at the top. Now, these motifs, loop and bulge, are not just there to provide the flexibility to this RNA, but in physiological sense, and especially how the virus replicates and infects the cell, has a lot to do with the loop dynamics as well as the bulge. Because if you express the mutants that lack that can disrupt the bulge or loop motifs, you see remarkable change in the ability of the virus to replicate. And some phenomenal experiments have been done on this this specific RNA molecule, and I welcome you to look at, I think, significant work by the Hashim Al-Hashimi's lab in University of North Carolina. And he has applied NMR-based methods to basically probe the dynamics of this molecule in various kind of states. So when we chose this molecule, one of the reasons we made the choice is not only its biological significance and small structure, but more importantly, the conformational diversity that is observed in its structure. In my understanding, I think this is only one of the few RNA molecules that has been shown to bind to so many different kind of molecules. So on this slide, if you're looking on the left, many structures of the TAR RNA are shown. At the center, you are looking at the experimental APO structure, and this is the PDB code for the experimental APO structure. And then on this circular arrangement, you are looking at the same RNA molecule in different conformations, but bound to various kinds of molecules. So you have fairly small molecules on this side. And if you are paying attention, this one, this one, this one, and on this side are very large cyclic peptides that can bind to this RNA. And they cause various degree of conformational change in this RNA molecule. And this is fascinating and useful for us as we try to do simulations with one of these structures or more of these structures, primarily because we know molecular dynamics is very sensitive to initial coordinates. So we want to start with as good coordinates as possible that are experimentally resolved instead of guessing the positions of atoms. So if you map the location of these various ligands, I'm showing you on the right-hand side in a single map, these green spheres are the centers of masses of various kind of small drug-like molecules that have been found to be bound to tar RNA in experimental structures. And the magenta color spheres represent the peptides that have been found. So most of the small molecules are near the lower helix, shown in cyan, and most of the peptides are near the helix 2, which is shown in blue here. So some of the analysis, you may be wondering the strength of the binding. So dissociation constants for these various kind of ligands are in the micromolar range. Some are weak binders, some are fairly tight binders. The buried surface area between these ligands and the tar RNA molecule is on the order of, again, 400 to 1700 angstrom square. And if you wonder about how much conformational change is there, then the RMSD is somewhere between 5 to 8 angstroms. So what we did was we did not want to choose one structure over the other, and moreover, we are interested in exploring the general conformational dynamics of this molecule, try to understand how RNA molecules behave in solution. So we started by doing simulations of every single structure that's shown on this slide. We started simulations with the experimental APO structure, and then we created many APO structures by deleting the ligands from them, as well as conducted simulations by keeping ligands present. So we conducted all these simulations and generated, I believe, to date, one of the largest data set on these RNA molecules, somewhere in the range of 60 microseconds of all atom explicit solvent simulations. And these data sets are available to the scientific community at this website. And there is a DOI I can provide later if you need to access the data set for, because lots of people we heard are doing machine learning based analysis. We haven't attempted to do any machine learning on any of the conformations we have sampled, but anyone is free to download the data set and try some of their methods. So let me quickly describe what we find by simulating all of these structures of tar RNA. And I'm going to describe some of the global changes first, followed by local changes and their coupling. So one of the common beliefs that we have studying proteins is that when ligands bind to biomolecules, typically they stabilize the structure. And we wanted to see if that kind of theme holds even for RNA molecules. And indeed, it does to a large extent based on study of this tar RNA molecule. So if you look at RMSD distribution in the unliganded state and the liganded state, you clearly see liganded structure shifting toward a lower RMSD value, meaning that globally the overall RNA structure got more stabilized in the presence of the ligand. And then we can map these kind of mean values in the liganded state shown here in the light color, and the mean values for the liganded state shown in the darker color for all tar RNA structures that we simulated. And we find across the board that most of the ligands try to stabilize the RNA structure. So that's kind of consistent with what one would expect, that ligands somehow add to the stability of the RNA molecule, except one of those cases, which is shown here with an asterisk on it, where we see liganded state more flexible than the unliganded state, and I'll show you why that is so. Then we looked into, at the next level, so outside of the global RMSD comparison, these two helices that I spoke to you earlier about have been probed at their rotation using NMR methods. And it's known that these helices also become more stable in the presence of ligand. So if you take a vector going along the axis of one helix, another vector, measure the angle between these two vectors, we find that in the unliganded state, these distributions are much more wider and shifted to the right, meaning that there's more flexibility between the helices. But as you add the ligand, or if you conduct the liganded simulation, you tend to see the distribution become narrower, meaning that fewer values of this angle are sampled, and in fact lower values. So it also kind of rigidifies the helices a bit. So then we next probed what happens at the where is this coming from? So one can analyze residue fluctuations for every nucleotide in every structure. So I'm showing you these maps where x-axis shows individual nucleotides in each of the TAR RNA structure, and y-axis shows a difference in the root mean square fluctuations compared to the unliganded state. So if the ligand stabilize, you are going to see negative values of RMSF, which we see in most of those structures. As you look at this one, this one, this one, this one, this one, this one. But there are a few cases, as I pointed out, in one of those structures where we see positive RMSF values, meaning that a higher or increased flexibility, same in this case. But generally speaking, ligands seem to stabilize not just the helices, but across the board, the entire RNA molecule is stabilized, as indicated by negative RMSF values for all of these structures. One can look at the flipping of bases. So here is one of those bases that in the unliganded state freely flips because it's not stabilized by anything. But in the liganded state, it's significantly stabilized and it does not flip. And we see this kind of stabilization again in many other structures. But let me show you some of the bizarre things we observed. You can call them rarely observed transitions or structures in the TAR RNA. So in one of those structures of TAR RNA, where we start with ligand bound state, we observe that over the course of the simulation, a very large scale conformational change happens. For example, if this was to be considered palm of a hand, then somehow you see the ligand molecule squeezing between it during the simulation. And this is one of those cases where we see different behavior than expected. So even in the presence of the point that I'm trying to get across is that it's not the binding of the ligand itself that stabilizes, but even when ligands are bound, this is an experimental structure, even then we can observe way more conformational changes as we see. This leads to a significant increase in the buried surface area as expected, more atoms are closer. And then this other example is exactly opposite of that. So here ligand was present, RNA was more open, it became more compact. But for a different ligand, we observed that RNA initially was more compact and it became way more elongated. And this has to do with some conformational rearrangements that happened due to insertion and flipping of or rotation of the ligand itself in the binding pocket. So ligand doesn't occupy the state that's precisely in the experimental structure, but it can readjust during the simulation. So these were interesting observations that were different than expected. We also probed if we can observe flipping of bases between the liganded and unliganded state, and somehow they are different. So earlier I showed you that the bases flip less when ligands are bound, but this slide is trying to show you exactly opposite of that. So here is this 4 pair of bases somewhere in the middle of this RNA molecule, U23, U25, and C24. These 3 bases we try to track. And if you look at over the course of simulation, one of the dihedral angles that kind of characterizes whether the base will flip or not. In the initial case, we find that the base is in the outward conformation. So this light gray rectangle is the range of angles within which, if the angle is observed, the base would be considered inward, otherwise it would be considered outward. So initially it was in the outward conformation, but we found irrespective of presence of ligand or not, it could go inward. Similarly, in these 2 other cases, we start with an inward conformation, And we find that irrespective of the unliganded or liganded state, the base can still flip. Similarly in the third case. So we were intrigued by generally these observations that ligands are somehow able to cause even more flexibility, although generally ligands try to stabilize the RNA molecules. And same for bases, that bases are generally stabilized, but there are cases where even in the presence of ligand, these bases could flip. So we undertook two further studies to focus a little bit on applying some methods to understand how these conformational transitions are coupled with ligand binding. One of those studies is shown here. We chose one of these small molecules that can that is somewhat relevant, and its KD is known, it's less toxic. It can be well studied using these pulling simulations. So we carried out constant velocity steered MD simulation. I give some important information on general questions that are being asked on steered MD. It's a fairly old technique, but still very, very relevant and useful method to understand ligand dissociation. And I can go into details of why we choose steered MD over other techniques. So we ran lots of these simulations. You have to be extremely careful to make sure that the ligand fully dissociates and you get force convergence toward the end. And then you can collect the work of dissociation from each of these trajectories and make a distribution. So some of these trajectories show as we dissociate the ligand along the same reaction coordinate, we get fairly low work values, but then in other trajectories, we can get high work values. And earlier in one of the talks, I think we heard about the well-known Jarzynski's equality that connects the non-equilibrium work to equilibrium free energy change. And it just so happens the nature of this equality says that we are doing exponential averaging of these work values, which means the values that are in the tails of distributions, especially these lower values, are going to contribute significantly to the overall free energy change. So we can take the work data and convert it into a free energy profile. We try to do it using standard Jarzynski equation and a cumulant expansion of the Jarzynski's equality that's been previously proposed by Schulten and co-workers. And it improves the convergence of the PMF a little bit. You can see in the dissociated state, the free energy is higher. In the associated state, free energy is lower. But we were not so much interested in necessarily obtaining a value for free energy. This free energy value is useful. I mean, we can back calculate the dissociation constant. We can compare with the experimental value, which is anyways known. But we are more interested in as to what happens in these unique trajectories that require lower work to dissociate the ligand. So we further probe these details. I'll point out a couple of unique observations. So the ligand is shown here squeezed between a bunch of nucleotides that are surrounding it. And the two nucleotides that I want to draw your attention to is C24, which is right there shown in blue, and U23, which is shown in light orangish or yellowish color. What we observe that in the simulations that lead to a lower work, we see unique arrangements in the conformation of this base C24. So as ligand tries to dissociate out of this binding pocket, initially this base was somewhere outside, a little bit outside the pocket. And as soon as ligand moved out, the base rotated spontaneously inward and occupied the space that was roughly occupied by where the ligand atoms were. On the other hand, in the higher work simulation, this is one of the highest work simulations from the distributions I was showing. So if you take one of these trajectories at the top, we find that there's no such conformational change in C24, although ligand dissociates somewhat in a somewhat similar manner. This contributes to a difference in work values. More importantly, this higher work, I believe, is coming from the orangish nucleotide, where it comes in the way of the dissociating ligand. So there is obviously work required for opening this door or moving the atoms out of way, and that adds to the overall work of the simulation. Then we compare one of the dihedral angles of these bases, and we clearly can capture these transitions that in one of the transition is observed in the higher work simulations, SMD dissociation simulations, and the other one is more observed in the lower work simulation. So this was intriguing to us, that there is this coupling of ligand binding, and it could lead to more quasi-equilibrium kind of dissociation of the ligand, as opposed to causing significant non-equilibrium as observed in higher work simulations. So you might wonder whether these ideas apply to larger ligands. So I won't go into the detail of this other work, but a recent study that we did has appeared in Biophysical Journal this past month. And we try to apply similar kind of techniques to understand how peptides bind to an RNA molecule. It's an arginine-rich peptide. We study multiple pathways that are shown here. We study the role of restraints. We study dependency on ensembles. Some other reviewer curiosities about whether umbrella sampling will be a good technique, or how can you optimize reaction coordinate using string methods. All of that is done, and I welcome you to refer to this paper. But let me spend a couple more minutes before I end my talk on another study that we have carried out on understanding the flipping of bases in RNA molecules. So for this particular case, we chose a different RNA molecule that's double-stranded, and where base flipping is more experimentally characterized. So this is a long RNA molecule, longer than the TAR RNA, double-stranded, well-base paired. But here, somewhere in the middle, one of these bases, A18, is known to flip outward. And this transition is basically related to how certain enzymes are going to make modifications on the RNA molecule. So I'm not going into that detail. So the title of the slide says we apply path sampling and likelihood maximization based methods. And we extensively tested many different kind of CVs. We chose dihedral angles that have been in the literature, many distances between bases, across the bases, many angles that we define, number of water molecules, different kind of stacking energies. And we kind of tracked all of these parameters to see how well they distinguish between the initial and the final, meaning flipped in versus flipped out states. One of the older parameter has been proposed in an earlier work in 2003. And this is a pseudo dihedral angle that can be defined by pairing this group of atoms and tracking how this base will. So we try to use that older parameter and see if it can well distinguish between initial and final states. And we found, yes, indeed, it does. I show you one of the seed trajectories for these calculations, where we observe a sharp transition along this older parameter. We choose some shooting points. We apply these methods by Peter and Trout that was well described, I think, by Srebny Trapter earlier in the meeting. So I'll skip these details. The key idea in this likelihood maximization method is you can, it allows you to build many models of reaction coordinate by picking single CVs, double CVs, triple CVs, and we did all of these models, roughly 300 of them. And then using a Bayesian information criterion, we can rank them and see which ones are good, which ones are not. And then we eventually come up with our reaction coordinate that turns out to be made up of two unique kind of CVs. One is a distance, stacking distance between the bases, and another is a special type of dihedral angle that captures. So combination of these very well captures the opening of this base. We can project the free energy on our reaction coordinate and look at the transition state, the outward state, the inward state of the base. But more importantly, I want to point out that we discovered this metastable state where we are finding a very unique kind of arrangement of bases. Like in the initial state, only two bases are interacting. In the final state, only two bases are interacting. But in this metastable state, we observe three bases kind of cross interacting with each other. And a key effect of this on the global structure of this RNA is it goes from this magenta conformation to blue. So there is a huge conformational change that happens as these bases rearrange. And this was we were really surprised how the global and local conformational transitions that we observed using path sampling are connected. So with that, I'm going to wrap up my talk and thank two of my students and one postdoc and one student. Dr. Lev Levintov contributed to this work significantly, carried out all studies. And the path sampling work was assisted by Dr. Sanjay Paul, and he was attending, I think, the meeting earlier. our studies that I showed you, 3 kinds of studies. One was on general conformational dynamics of tar, was published earlier this year. On the small molecule ligand, the steered MD was published this past year, and the more recent peptide one was published last month. And the reaction coordinate one was also published earlier this year. So with that, I want to thank funding agencies that supported this work, NSF, NIH, and the research computing through NSF, as well as University of New Hampshire. I think everyone is ready to brainstorm some, and I'm happy to answer any questions if there are.
So thank you, Harish, for a nice work. So the session is open for discussions now. So we'll take up some questions. We have some time for a couple of quick questions. So those would please unmute yourself and you could ask your questions.
Hello, am I audible?
Yeah, maybe you could introduce.
So my question is, you have put this reaction coordinate where you combine the distance and multiply a factor with it and a specific dihedral, right? Hello?
Yes, I can hear you.
Yeah, so my question is, since this distance is a linear variable and the dihedral is a sort of a periodic variable, so how can you combine two different variables of two different nature? For example, if you have a phase shift in the dihedral, then that may change your reaction coordinate.
I get the question. So yeah, you can read the manuscript, I think, and as I said, previous work by Tarapter group, you can normalize the variable and make them dimensionless, I believe. So that's how they are combined.
Yes, Ramani, you want to ask something?
Yes, thank you, Harish, for a very nice talk. I was wondering if you have checked for the kinetics along the reaction coordinate that you have got for your base flipping, and what kind of time scale do you get here?
Right. Well, the thing is, there are no good experimental measurements, first of all, for the system to really know the rate constant. We applied some approximate models. I don't have the numbers with me right now, but they are reported in the thesis of Lev. But yeah, we did some kinetic calculations. That wasn't one of the primary priorities, I think, for us to match the rate constant here. We were more interested in finding a reasonably good reaction coordinate that could capture this transition, and more importantly, can such reaction coordinates, I mean, it's a brainstorming question, can it be translated to other RNA molecules?
Okay, thank you.
Thanks, Ram. So, Peter?
Yeah, hi. Yeah, nice presentation. I was indeed also struck by this same question. So, I mean, the first question that comes to mind here is, so there has been studies in the literature also on DNA and DNA-based flipping, and how do these two processes now compare? So, can you say something about the kind of a general reaction coordinate for these type of biomolecules that do stacking of base pairs?
Right. So yeah, a few different studies, I think, on DNA molecules as early as, I think there was a study in 2003 by Aaron Dinner and Arup Chakraborty. I think very early work on DNA, where, well, in their case, I think they create sort of an artificially paired trinucleotide pair, examine the different kind of energies, and they do describe the importance of stacking energies. We did investigate all the stacking energies in our collective variables, and we do not find them. Again, everything is a factor of force field. Force field contributes heavily to the stacking energies, and stacking energies have, for nucleic acids, especially for RNA, have been optimized over a period of time. So I don't know how one makes fair comparison. You know, with previous observation and the newer observations with the newer force fields. But to answer question about general reaction coordinate, I imagine that this reaction coordinate, again, we haven't tested it and it remains to be done. But since it depends on the interbase distance and a particular dihedral angle, these two are very generic parameters that are applicable to any of the RNA molecule that you can imagine. They are not. So we were very curious if water molecules are going to play a huge role here. How stacking energy, and we were somewhat I think encouraged that these two kind of variables that we believe, solvent dynamics as well as the stacking energies, could be central, and then it becomes real hard, I think, going from one reaction coordinate to the other, because as the base type changes, the stacking energy changes and the water molecules are different. So I believe this kind of reaction coordinate, which we explicitly found through this extensive testing, could be useful, I believe, for other RNA molecules.
Okay, thanks very much. Can I actually ask a follow-up question?
Maybe one quick question, Peter.
A quick question. Yeah. So, of course, this is already a lot of work, I understand. But did you also do re-evaluate the quality of the reaction coordinate by an additional committer test and committer histogram of this particular reaction coordinate?
Yes, yeah. I don't have the committer plots here, but I can show you some kind of supplemental data that's in the paper you can look at. So, for example, one can analyze the shooting trajectories that are committing to the reactant and the product states. And you can see if when you project along the reaction coordinate, if you see convergence toward your stable states. And this is just one plot. There is more like this from many other trajectories shown.
Yeah.
If this is what I think the
yeah, and these are very expensive, of course. So I understand.
Yes, indeed.
Okay. Okay. Thanks very much. I'll
thank you. Thank you very much. So maybe if there is further questions, you can just write it in the chat here, and or you could write it to Harish directly. So Harish would be willing to answer the questions for you towards you. Yeah. Thank you, Harish. Thank you for a wonderful session. Yeah. So
thank you so much.
With that, we conclude this the talks in this particular session. So thank you. I thank all the speakers for a lovely and wonderful session. So thank you all. So I hand over the session to the next. Thank you.
Thank you so much, Padmesh. I think now it's the highlight, the brainstorming session. So Professor Perapter is there, Professor Layo, Alessandro is already here. Alessandro, are you?
Yeah, I'm here.
Okay, yeah. And now the dais is yours.
Yeah, well, I'm very, very happy to be with you, even if unfortunately only virtually. Let me say that I really keep my finger crossed that the next RARE meeting will be held live in India again. I really look forward to come again to your beautiful country. We all keep our finger crossed, I think, because I am one thing I'm pretty sure is that we all had enough of variants and things like that. We had enough variants for the time being. Okay, so together with Srabani and yeah, also the organizers, of course, we prepared a list of topics which we would like to discuss with you. I think that the list of topics that we prepared would be sufficient for a brainstorming discussion of 5 days. So I'm not sure that we want to stay online until next Wednesday. So we will have in some manner to concentrate on some of the topics which we listed. And so we decided to do like a small game between me and Srabani, in the sense that we choose a topic each, Of course, for me, it's an honor and a pleasure to ask to Srabani to choose the first topic for a discussion, and then I will follow afterwards. Please.
Thank you, Alessandro. I actually decided to pick up the first topic, which is on the collective variables. And as expected, when the title of the conference is machine learning tools in enhanced sampling, obviously the first topic that has to come to your mind is the finding of collective variables. And now it is quite well understood that yes, it appears from the literature and from the talks that machine learning is really becoming useful in finding collective variables. And these are important not only in the full configuration space, but also in very critically chosen latent space as well. But what we haven't seen, or what really would be something nice to say, is if machine learning is going to replace all our intuition or all our knowledge about model systems and statistical mechanics and everything. So in that note, let us start the discussion, and let us say that, the first thing first, do we have a complete set of collective variables even for a single problem, irrespective of whether you have a biased simulation or unbiased simulation? So there are 3 points here: complete set, whatever they mean, and then whether they are applicable only to unbiased simulations or they are applicable to biased simulations as well. So I think Omer Walson talked a little bit about how to use the bias simulations, but I would welcome your comments on this.
I don't know, maybe I can give it a try to start the discussion. I mean, you asked for a complete set, but is it not more logical to ask for a minimal set? For what is the minimal set of collective variables that you have to use to cover?
So what I meant was, for a given choice of the number of collective variables, that is whether it is giving me a complete description of the relevant length scale and the time scale.
So maybe I can elaborate a little bit on that, because so the first thing is actually being sure that the set from where you make your choice is in some sense complete. And this complete is also something which requires a little bit of discussion. So what do we mean with complete? I think, do we have quantitative manners of saying if a set is complete? Then after we have decided if a set is complete, and this is in my personal opinion and also personal experience, not so simple, one can actually try to see if it is possible to basically describe the system with less collective variables. Say that I have a complete set which includes, I don't know, 200 SOP coordinates, SOP features, or all the dihedral angles, or all the contact between heavy atoms in a protein. So these are far too many. This is possibly complete, but then, okay, and then so the next question is, of course, is am I able to obtain a description of the same system, with less collective variables, let's say without significant information loss somehow, no? So this is something which, in a way, these are two different things. And for example, these are two different things that both, in my opinion, deserve some thought and discussions. Like, for example, so do we have a complete set of variables for describing a biomolecule? Question number one. Question number two, do we have a complete set of collective variables for describing a generic, well, let's say complex chemical reaction? And moreover, do we have a complete set of coordinates for describing, I don't know, a conformational change in solid state physics or in nanoscience? So clearly in each of these fields, somebody would, so I would have something to say, but maybe others have other opinion. Maybe we can start from the biomolecules, where I think our heart lives mostly. Can somebody comment on?
Yeah. Well, like just to specify, or how do you to come up to continue on this? You mean something else than just the Cartesian coordinates? Yeah? Because of course the atomic coordinates are in principle sufficient to give you a complete description. So you want to have already a reduced set of coordinates. For example, these SOAP coordinates or other features.
Yeah, for example, are you aware of something like the SOAP coordinates, but for describing the solvent around the protein? Because of course you don't want to describe all the solvent explicitly, I guess, right? Because you have of course permutational invariance. So do we have, did anybody try to use SOAP or SOAP-like or atomic symmetry function or something like to describe the solvation shell of a large protein? Not to the best of my knowledge.
Gerhard wants to put in his comment. Gerhard, can you mute yourself?
Yeah, hi.
Gerhard, nice to see you.
Hi, nice seeing everybody. So, two things, yes. We have certainly used symmetry functions, although not for proteins, but for obviously smaller molecules. And we found them to work quite well, but clearly scaling them up to where so the solute is itself rather complex may require additional considerations. And maybe to the general question, obviously this is not an area that I'm an expert in, but we do have experts here in the RARE 2021 meeting. So this question of going from a complete to a minimal set is certainly a question that machine learning has tackled in this and other contexts, for instance, by using variational autoencoders. So it's at least, it may not tell you what the minimal set is in a simple human understandable functional form, but if you can squeeze it down in this whatever double pyramidal architecture to very few features, you have an idea that there is an effective representation. So those are my two little comments, and I stop here.
I think there is one comment from the participants. Shumon raised this point that is it always necessary to find some global slow modes if you are really interested in some specific local conformational change or the local modes controlling a catalytic reaction in enzymes? So how do we understand if that global slow mode is going to be important at all for the process of interest? So I float this and I ask Christoph to go ahead because you have raised your hand. We will take these 2 points.
Yes,
together.
so I just want to comment on what Gerhard said. Actually, what you did, Gerhard, using this symbolic regression, I think it's a step in exactly that direction to identify the important degrees of freedom and represent them with analytical expressions. You know, sometimes it's hard to understand what they mean, but in some situations it might be possible to get a meaning out of these analytical forms that you that you get, right? And then before I turn over to Gerhard, perhaps, let me also comment about the slow modes. I mean, in rare events, it's often the important degrees of freedom are not slow. They are actually quite fast, because when the reaction occurs, it occurs quickly into certain directions that are not necessarily associated with slow modes.
Yes, absolutely. So Gerhard.
Yeah, so great. I think these are actually, thanks, Christoph. Two important points, and I didn't want to emphasize this too much, but I'm really thankful that you raised this. That one of the things that we are learning is that with machine learning tools, indeed, you can derive functional forms. And I think in Peter's talk, you could see committer isosurfaces that had functional relations, and actually they work in our hands. This is Henrik Jung's hands and Roberto Covino's hands. They work better than the neural net representations because there are good regularizations in there. And the functional forms in that case turned out to be quite suggestive in the sense that you could recognize in the expressions terms that do look like temperature. So clearly we're not there yet, but with these baby steps, at least there are indications that this actually works. So I think that this is really something that we will certainly see more of. We see it in other fields as well, that is to go from just AI as a black box to AI that looks a lot more like the theory papers that we have seen published.
Can I ask a question to maybe, so because to me, one thing that is always a little bit still obscure, and where I think there is still some work to be done, is in quantifying. So, well, there are, of course, when you do a dimensional reduction, and this you can do it in many different manners, like Gerald's approach or others. So you sort of, well, in a way, so there is, let's say, an exact manner of telling if you have done things right by comparing, for example, the relaxation dynamics. So, for example, the transition times between your metastable states. So, but this thing is very often, well, too much or too difficult for practical application. So, are you aware? So there are other manners which are a little bit more hand-waving or maybe more practical to assess if your dimensional reduction is at least viable, without, of course, if I know all the dynamics and I do all my Markov state modeling, and then I am able to recover everything using this and that, this is great. But do you have other manners to say if your dimensional reduction is meaningful? For example, in your approach, Gerhard?
Yeah, I think this is obviously, I think everybody is struggling with this question. So the way we do it is by making predictions, and then testing the outcome on the fly. So it's like we have what economists would do all the time. We're making bets, and our bet is our computing time. So that's the money we put in, and we get the return is by discovering new things and confirming the quality of our model. And so in that sense, this AI-driven form of path sampling that I did not present for various reasons, but Peter briefly alluded to, because it's a collaboration with Peter and now also with Christoph, is a closed loop where the quality of your prediction improves as the model improves, and you can constantly test the quality of the model against the outcome of your various trials. And I think that is again in looking forward, hopefully something that we can also use in other types of applications, for instance, free energy sampling applications. So that the same idea that there is direct feedback from the future runs on the quality, on the assessment of the quality of the model that you have.
Yeah, so I sort of noticed that there are few important comments on the chat. So maybe I would suggest that if it's not strictly necessary, is to simply
yes, I was going through it. So there's a question from Pallab Datta, and this is directed to Chris Delago. Nature should take at least a least resistive path to go to the product state. But the slowest degree of freedom may be the most hard path to follow. Do you have any comments on it? It's there in the chat box.
Yes, I see it. Well, my comment is that what I said actually was not that the slowest degrees of freedom are always the ones that are the important ones. It's rather in many cases the opposite, that transitions can actually occur quickly. It's just the waiting time for the transition to happen. It's the rareness of this fluctuation, but when the fluctuation occurs, it can occur quickly. So I don't think that it's correct to think about slow modes in the context of rare events.
Okay, thank you. And I would now request Shumon Chakraborty to pose his question regarding the hidden degeneracy or entropy of CVs. Shumon, would you like to come in, please?
Yeah, okay. Hello, yeah. So in my experience of using, so it's traditional, it's very common to use CVs like RMSD, particularly in the context of proteins, for example. And it is well known that CVs like RMSD suffer from this huge problem of degeneracy at large values. And my experience, for example, I have encountered systems where at large values of RMSD, at the same point and on the free energy surface, there can be largely different conformations, which are actually separated by large barriers in an orthogonal coordinate. So I was wondering whether, so such CVs where you have a distance metric from a reference structure, obviously that suffers from this problem of large degeneracy. So whether it is at all recommended to use such CVs, and what would be the other ways of detecting the other structures in the orthogonal direction? That is one question. And the next, the other point was that, in general, whenever we are using such RMSD-like coordinates for enhanced sampling, we have this entropic bottleneck kind of issue that it's very easy to go away from the reference structure, or let's say you have even coordinates like coordination number, which also suffer from degeneracy at coordination number 0. So let's say I want to go from a specific structure to another specific structure, where the intermediate region can be a large entropic region with lots of degrees of freedom. So it will be easy to break the structures and go into this huge entropy region, intermediate region, but then again, it becomes difficult to converge to the low entropy specific structure. So these kind of issues that we have been it's very common to encounter in biomolecular conformational space search. So I would request some comments on these aspects. And also, I guess this is pretty common in IDPs in case of, it's a generic question that what would be a good CV for intrinsically disordered proteins. where there is no unique reference structure to even talk about.
So do we have a volunteer for this issue?
I have a question, Suman, to try to understand. Is RMSD the right coordinate to look for stable, free energy minimum? Not right, because
right. So RMSD is a good. RMSD can be as good as only to describe something when it's similar. So I can only, let's say when RMSD is very small, I can say it's very similar to that structure. But when it comes to the large RMSD values, there is no. It does not serve any purpose as a CV in some sense, because it cannot characterize any specific structure. Yeah.
So for the trip gauge, let's take that as a toy system to look at folding and folded in intermediate states. Even RMSD RG surface of trip gauge, you can't see the pathways. So there are two pathways, like Peter's work and so on. So you can't really see them on the RMSD RG space. So you need, I think, RMSD and something else to really see these, So
right.
I think so. Depending on the problem, I guess RMSD is a good coordinate for enhanced sampling. Maybe not really for. I think possibly we shouldn't ask this question of whether, because once you define the coordinate and calculate the free energy along that coordinate, you're assuming that you can separate the important states through that coordinate, right? So I think what you get is at the end of the day, what you asked is what you get, I guess. So that's why
right. Maybe I'll put two counter examples just to respond to that. So yeah, for unfolding processes, it's probably what you said makes sense, that when it unfolds, it's something else. Yeah. But let's say you try to go from an alpha helix to a beta hairpin, where your reference structure is alpha helix. So your beta hairpin will also have a large RMSD, and an unfolded structure will also have a large RMSD.
Right.
So how do you know when it's folded to folded, then is RMSD is a good coordinate? So so it depends on from where to where we want to calculate this delta G. So when it's unfolded state, probably, so again, how we are doing this partitioning, that how you want to characterize these states, that probably becomes crucial for the choice of the CV, I guess.
Yeah, in my personal experience, not even for folded to folded, the RMSD is a really good collective variable. There were other people that wanted to talk before me, so sorry for jumping in.
Okay, Gareth, would you like to go first?
Yes, I can do. So I had sorry to get away from the RMSD, and maybe I'll come back to that one in a second, but I had a comment on the slow degrees of freedom. I think, and maybe I'm wrong or being deliberately provocative, but it's irrelevant whether the degrees of freedom are fast or slow. If you're calculating a free energy surface, you need to average over all of the other coordinates in the system. So if you're not speeding up all of the coordinates, you're not going to average over the all of phase space, and the free energies that you get out are wrong. The ensemble averages are wrong. So you can't just break this down into say which are the right coordinates to accelerate the process I'm interested in, unless all you're interested in doing is extracting information about the kinetics of a process, in which maybe you can. But if you're interested in getting the free energies, you have to average over it, I think. In terms of the RMSD, there's a lot of research literature, and what a lot of people have been doing with machine learning algorithms and path CVs and various things is using multiple RMSD values in their simulations. And you either use some function of that in function of multiple RMSD values in a path, or you can just use two RMSD on the axes, and that sort of gives you slightly less degeneracy as you go away from the configurations. So yeah, those are my 2 points.
Thank you, Gerhard.
Yeah, so two points. One to Christoph, who raised, in my view, also a very important issue, that time scale is not everything, and I just bring that up. I mean, as my favorite example, the slowest degree in protein folding is not often protein folding, but is some proline isomerizations that usually you're not very interested in because your particular protein will fold in the trans form and it may not fold in the cis form of a particular protein. So there is this very, very slow phase in there. So keep that in mind. Second one, I think this question of RMSD being a poor coordinate away from even the short distance away from the most highly ordered state, I think is a very important one that we've probably many of us have run into. And I think it is an issue that deals with entropic states in general. Whenever you have states that have high entropy, you have to deal with this issue. And of course, one way of dealing with it is by changing coordinates, using different coordinates. And for instance, for an IDR in the unfolded state, configurational reconfiguration may be the slow coordinate, and with reporters, the end-to-end distance, radius of gyration, and so on. And so you would have to include that. So it's, I think, and I saw a comment from Jayashrita in the chat raising this issue. I think I totally agree with her. It's just not possible to have one single coordinate when you have an enthalpy to entropy transition.
Okay, so that brings us to some level of discussion regarding the collective variables. And I think I will read out one comment by Peter. And he says that RMSD is great for identifying structures that are close to a reference, which is exactly what Gerhard mentioned now. But he also adds that indeed a path variable based on RMSD is a great coordinate. And as a member of the path sampling community, I think that is something I also second. So Alessandro, you want to go for the next topic?
Well, I think there are still few hands raised, and in particular, there was an important comment by Jayashrita that I think, I don't know if he raised with a short question: do we really need global CVs? Let's say that we have a reaction A to B that can proceed via two paths, ACB or ADB. In such a case, do you really need the global CVs, or do you want local CVs that enhance fluctuations in a given basin? So as a general suggestion for the discussion, I would actually ask, maybe, since we are many, and so to try, well, we can write, to make the question directly. Otherwise, maybe some relevant questions simply get lost because they are written in the chat, then there are others coming and we don't understand anymore what's going on. So I don't know, is anybody willing to reply to this specific question before we move?
No, I think I can put in, because in my lecture, Jayashrita, you might have seen that I was looking for some starting state A and ending state B. And in that particular case, as I have mentioned, that a single collective variable for this was not possible. And in that example, it was because you had not only conformational transitions, but things like a change in coordination number around a metal ion, which could not be captured using classical simulations, then actual bond breaking and making steps, which needed those conformational fluctuations to prepare them in the right process. So the only way that we could solve and get to some kind of a solution is because we had multiple reaction coordinates for each of the small steps that we have developed. But I do see 3 more raised hands. So whom should we take first?
I think Amish has started earlier, so maybe you can.
Okay, Amish, please go ahead.
Thanks. So very interesting discussion. I wanted to bring together something that Alessandro started off by saying, and then combine that with something that Peter said. So this notion of this complete set of collective variables, and what does complete even mean? And then Peter introduced this notion of perhaps more important to think about a minimal set, right? And perhaps, what is a complete minimal set, right? So this is what, one of the things that I think we can all agree upon. How does one test this, right? And so in my experience, the thing that I've resorted to is anytime I have a process that I care about, and these tend to be much simpler processes than many of the ones that are discussed here. But with this caveat, we have two basins. If you just think about the simplest of enhanced sampling techniques, umbrella sampling, we start all the umbrellas in basin A. We start all the umbrellas in basin B. Do we get the same free energy profiles? No matter if we have a complete minimal set of collective variables, then they should agree entirely, right? And this is
clearly
necessary, right? But is this also sufficient to say that we have a complete minimal set? So I wonder if people have thoughts on this. And I guess a little bit of get on my soapbox for a second. I feel like, not everyone sort of does this exercise, right? Of ensuring that you have the free energy profile, that it's reversible, and that I know it takes twice the amount of time to do this, but often it can be very insightful to do this, and it often teaches us about orthogonal variables that we're missing in our initial class.
Yeah, I think if I understand, I think what Amish is trying to point out. So I think it most likely what he's trying to say that if you do not have really a good CV, like let's say you have two different initial configurations for the same set of umbrella sampling, you might end up completely, and that I think most of us most likely have experienced it. Like you will basically get completely different free energy profile, and barrier heights and all these things can get completely different. And I think it's mostly to do with that whether there are other CVs around which we are not sampling enough when we are trying to look for two different basins, and we have decided that at the very beginning that this is going to be my go-to CV from the day one. And I think that is what Amish I think is trying to point out.
Yeah, thank you, Jagannath. Maybe take Peter's.
I had one more comment. I think since what I'm following is that Gerhard had started all this looking at single molecule pooling experiment, and now he's doing integrative models of this big big macromolecular assembly. So the question that I really had is that in this particular perspective, what do they think that this CV discovery is going to help? Like, is it going to be practical for this large scale assembly that you are looking at eventually? Are you going to take the entire pain of doing this neural net based approach to figure out a CV, and then you're going to apply it for looking at the integrated models?
If I can just answer, yes, absolutely. And I think that, for instance, I don't know if you saw the simulations of the nuclear pore complex that are out on bioRxiv. It's really, that's the thing now, to extract from these simulations, for instance, mechanical coupling. So that's what we're working on very actively. But of course, I can see where you're heading, that the tools that we and others, and many of here have developed for alanine dipeptide, how useful will they be with these big systems? But my first impressions are, I think many of the tools really do scale quite well. So this is not, so the thoughts that we have worked on for so many years and the ideas and the models they are transferable when you are willing to sacrifice a bit the rigor, and maybe at least in the first incarnation of these approaches. But I'm personally quite excited by this parallel developments that we have seen here at the RARE meeting, and great advances in the methodology, but also the ability to tackle increasingly complex systems.
Right.
And I think that the two aspects are coming together.
Okay,
Yes.
Jagannath, can we move over to the next question, or would you like to have something more?
No, I
Okay,
think,
then.
I think Peter has raised his hand for a while. I think he should.
Yes, Peter,
Yeah.
please go ahead.
I don't want to take up too much time. I mean, it's an interesting discussion. I mean, I just wanted to say that there are many ways to skin the goat or the sheep, whatever you want to do here. But so you can actually use global CVs or local CVs, and in one case, if you have a local CV approach, you end up with a network type description, like a Markov model, where there are multiple pathways possibly. And if you have a global approach, then you might end up with a very complicated neural network description of using, for example, an autoencoder, which has a nonlinear type of path description, which has exactly the same information, only in a different form. So, I mean, one of the questions that I would have is, how would you distinguish between those two descriptions? So suppose you have two descriptions, one which is based on an MSM type kinetic network with lots of different possibilities, and the other one is based on a very complicated high dimensional embedded space or a latent space in a autoencoder, for example. So how would you actually distinguish between those two? And that is a question that I want to ask to you. I mean, maybe it's not a big deal, right? Maybe they're both okay, and maybe even you can argue that a network description like an MSM is more insightful. But on the other hand, you can also use the tools that we heard from Gerhard, but also from other people to interpret the latent space of the autoencoder, and that would be also one approach to solve this. Okay.
I could comment on that, but maybe there was Anand that wanted to talk before me, then I can take the word.
Okay, Anand, would you like to go?
Alexandra, I think you can address this and then I can put my questions. It's fine.
Well, I don't know if, of course, it's very difficult to address this issue, but so the things that are basically. So in the issue of CVs, there are three things that one has to take into account. One, the fact of let's say, the CVs should be fully informative as possible. Then the CVs should be as few as possible, because one wants to do, for example, enhanced sampling, and then the CVs should be as interpretable as possible, no? And all of these three things. Yeah, all of the methods that one can imagine to develop are based on a compromise between these three three things. What I still think is still missing is a quantitative measure of let's say, so I don't say that it's missing a measure of quality, but a simple measure of quality. Here I was very, very happy to hear the answer by Gerhard about, which goes a little bit in the direction that I had in mind, but I still see some room for improvement there.
I just wanted to talk one particular point about Alexander's point. So I just wanted to ask, like, what do you think about this VAM score that people generally try to put to figure out the optimality of a particular CV that you have generated? So you're trying to look at the quality of the slowness of the CVs, and let us see how a bunch of candidate CVs. Do you think that the VAM score that Noe and other co-workers has put up, do you think that is a good measure that you can actually say that, you can actually think about a better CV than that, and based on that?
Yeah, there are also also the work by Pratyush, which basically allows in a way quantifying if one talks about kinetics, if a CV is better or not. So there are many interesting attempts in that direction. Yeah, I see many raise the hand. I don't know, what do? We continue with the discussion because I think it's so interesting. I would even have a general question to all of you at a certain point, which I would like to make, but maybe now there are other.
Okay, so let's go for Anand, because he has been waiting for quite some time. Anand, would you like to go with it?
So it's great that actually Alexandro answered something, and I think he mentioned that a CV should be full, which means that it should encompass as much as possible the coordinates, as many coordinates as possible. Like, you don't want one particle to be your CV position. And so and he said 3 different criteria, right? The other one is like as less as possible, and the third one is as interpretable as possible. And I have been thinking, listening to all these talks, when you have so when you have all these different projections that we are doing, right, like linear and non-linear, you have some projections are giving you many different basins. You can see that some dimensional reductions are actually giving you different clusters, and which means that they are actually giving you more number of states for the same cluster. So and then it has been off. So of course we know that they're not interpretable as much. Like we know, like when you project it using TSNE, what does it actually mean? But the other 2 criteria are getting fulfilled there, right? The third criteria is a challenge. I totally understand it. But then I also have been hearing across the different talks that it's not such a great CV, and I've been trying to put my head around that. Like, what, besides being the interpretation part of it, what makes it not such great CV? Like, can somebody shed light on it? Pratyush mentioned this. A couple of other people also mentioned this. So the whole idea of CV is that it gives you a lot of it identifies different states for you. You have to choose a CV that can identify all these different states. And if you are with certain projection, if you're getting many with one projection, suppose you do a PCA on a Swiss roll, you don't get that. But with another projection, you do get multiple basins or multiple clusters. So it does give you more information. It does give you more basins. It is encompassing the correlation matrix that you have written is taking into account maybe all the distances, maybe all the coordinates. So it has all the information of the system. The interpretability is the thing that is missing. But beyond that, what makes it difficult to have them as CV? I would like some thoughts on that to make like myself becoming more clear about it.
I can pitch my 2 cents.
Yeah, sure.
So
yeah, please go ahead.
So first of all, I think clustering is nice, but if it is not kinetically truthful, and that's the problem with RMSD, for example, right? The kinetic truthfulness is destroyed. 2 things have close RMSD does not mean the time scale to interconvert in high dimensional space is actually low. And the second point I wanted to make about interpretability, which goes to what Peter was saying about having a network, I think we need to come up with some general principles here, but one of them might be to think about local interpretability. Why do we want to interpret a latent variable type reaction coordinate? The same interpretation valid everywhere. For alanine, the peptide, yes, we can have one interpretation that is valid everywhere. But for complex molecules, there will be local patches of interpretability. And that again goes back to kinetic truthfulness. What does locality mean in a high dimensional system? How do you define locality? So in machine learning, people have been trying to come up with these local, there is an interpretability method called LIME, which is used a lot. And I think we should think about, well, we are working on it. I don't have any results yet. But so so if we could so we need a few measures, and as a community, we could come up with those. So Yanis gave a wonderful talk where he likes to talk about these diffeomorphisms. Any two variables, if they are diffeomorphic to each other, and the first thing there is 1:1, right? If they are not injective, then already some information is lost. So how to quantify diffeomorphism? I'm just throwing some words out there, but maybe with this. So kinetic truthfulness, which is the #1 thing that comes to my mind, and which is why I think PCA and RMSD especially start to become weak.
Can I just ask a clarity? So suppose a projection method, I understand the RMSD issue. If it is, you have multiple states of the protein, for example, and if a projection method is giving you those states, in one cluster, you are actually getting all the conformations that are similar, then where is this kinetic truthfulness or whatever you're saying is
yeah, so in the projection, if you simply define a Euclidean distance metric in your projection, count the distance between clusters, is it true to the interconversion time between clusters that you would have seen in the high dimensional space? How can you guarantee that? And there is a nice metric for this, the commute time that Frank and Cecilia introduced, for example. So are you preserving the commute time? If not, then something is wrong, right? Then you are getting wrong interconnectivity.
Well, I see.
The answer will be yes if your CV space is complete, in the sense that if your CV space does not imply an implicit projection, and therefore your diffusion coefficient will strongly depend on the position, then the distance in your extended CV space will be a good proxy of the diffusion distance, to my understanding.
So it's the kinetics that is coming into the way in these well-structured conformations that you are able to extract from, say, some of these more fancy NADRs method. Is that what it is?
I think so. I mean, yeah. I mean, we have free energy projections, but we have to be aware of the kinetics.
Yeah, we must be aware. But if you do clustering using, for example, as a metric, the RMSD, it's not that you are projecting on one variable. You are simply measuring your distance between all the atoms among which you are computing your RMSD, but you are doing no projection. There is no reference. So there is no projection if you do it, like if you do clustering in this manner. But then I have a well, maybe not a nasty question for all of you, but maybe Gerard wanted to comment. I see that he has his.
Yeah, Gareth Trebello has raised hand for a long time. He's waiting. Shall we give him a chance?
Yeah, sorry, my internet dropped out there for a minute, so I might be a bit behind where we are with the conversation. But there's this question that we have around CVs, and what is a good CV and what is a bad CV and so on. And whenever I hear this conversation, I'm always very provocative in the way that this. I think this conversation does not make any sense to me. It's nonsense. And please argue with me and explain why I'm wrong. I'll explain why I think it's nonsense. The CV you use depends on the problem that you need to solve. There is not some canonical CV out there that will work for every problem. I don't believe this. I'm willing to be convinced that I'm wrong, but you know, you have to find a CV and ask yourself, have I found out something interesting and meaningful about the physical system that I'm studying? And what you consider interesting and meaningful is on the problem that you're studying, the question that you're trying to answer, and so on and so forth, unless things have changed dramatically and we're all trying to answer the same common scientific question. So I'll throw that out there as a discussion point. Please fight me.
Can I take a first stab at fighting or actually agreeing with Gareth first and then maybe fighting with him? So I agree with everything you just said, right? But at the same time, I think there's a lot that we can learn in terms of the general principles that that we can distill from all of our studies on very different systems that are sort of might emerge as the best practices or good practices that a lot of different communities who are using these kinds of methods could follow, right? This is one of the things that we hope that a conference like this and a brainstorming session like this would give rise to. So I think that's what we're trying to do. And I think there's a lot of value to that.
I don't see any more hands raised, but maybe, oh yes, Christoph, please go ahead.
So I would just want to say that I think it may be very meaningful to look for a collective variable that describes reactions occurring in many different systems. I mean, unifying is always something that you try to do in science, right? So, for example, if you think about nucleation theory, the idea that you have a nucleus of a certain size and it is this size that is important for understanding how the transition occur can be applied to the condensation transition, to the cavitation transition, to the crystallization transition, to a large number of cases. And I think it's very useful to try to unify. So it might not work in all the cases, but the goal per se, I think it is a good thing because it will help us to apply ideas from one field to another, and that's, I think, a good thing.
Can I come back with a very quick reply?
Sure.
Just to keep the conversation going. So in a lot of the fields that you've spoken about, in nucleation, we know that there is a common denominator because there are inherent symmetries in those problems. A lot of the problems that we are solving do not, such as protein folding, they don't have those same fundamental symmetries. So sort of refining my question a bit, are we going to find these universal CVs if there are not these fundamental interchange symmetries and things like that?
Maybe I can comment on this. Can I quickly comment on this? I actually think, so without shifting to proteins now, I want to stay with the nucleation. One thing that we discovered, and this is purely because of the fact that you have done a CV analysis or a reaction coordinate analysis, I would say that actually more precisely, is that besides the size of the nucleus, it's actually also the structure and the specifics of what in case of crystal nucleation, the crystal is doing. And so this actually really can be used as a tool for discovery in that sense. And by discovery, you immediately get insights in the trends. And so this allows you also to create new theories and new predictions and trends. And so I really think this is one of the things that we can contribute as a community. And of course, if you can do the same for proteins, this would be, of course, I think, very useful also for interpreting experiments and so on. But okay, maybe I should not say too much about that now.
Amish, would you like to get back?
Yeah, I'll just add one more thing. So echoing what Christoph and Peter said, that even with proteins, I think, the one thing that we all tend to hide in our movies is that it's present everywhere, right? And that is the common denominator. It's the water, the solvent, and solvation effects and CVs based on those pervade all biomolecular phenomena, right? And so there might be something there that we haven't figured out yet.
Yeah, Alessandro, you want to go ahead?
Yeah, well, okay. So first of all, I would like to comment a little bit on what Gerhard said. So it is true that it doesn't make sense to look for the, let's say, holy grail of collective variables or the ruling collective variable, or you name it. But on the other hand, so where our community can contribute a lot is in providing quantitative criteria for understanding if a collective variable is correct or not for describing something. No? So this is something where we already contributed a lot, actually. No? And so this, in fact, brings understanding, like, for example, in the case of nucleation, understanding what is the correct collective variable brings understanding, allows developing theories. So, well, while searching for the most general and correct collective variable, I don't think it makes sense. But looking for methods which allow to quantitatively assess the quality of a description, I think this is our work. That's at least what I see. Then, I don't know, maybe we can continue still on that because it's very interesting, or I can...
I think there are some points which are related to these, but before that, Shumon and Gerhard have raised their hands. So Shumon, would you like to go first?
Okay, sure. So I just wanted to have, go towards different direction of comparing with experimental results. So I thought that I'll make this kind of provocative argument that even while we try to compare with experimental results, kinetics and so on, so even experimental measurements have their own CVs, depending on what they measure. For example, when you look into, let's say, protein folding kinetics, depending on whether you are using FRET or scattering or fluorescence, so you're measuring different things. It can be a local parameter, it can be a global parameter. So even at the experimental, for the experimental data, we have the sense of CV. And maybe while we talk about, when we try to compare our computational results with experimental findings, we should keep that in mind as well. So that was my comment.
Yes, Shumon, the point is actually quite well taken and was the topic of some other discussion points that we had. So it's good that you have already raised here therefore, that can be one of those criteria that you put into use when you test the CV for its goodness. So Gerhard, we are looking forward to your next set of comments.
Yes, I would just like to amplify a point that has already been made and make it maybe as strong as possible. I think we should always strive for transferable collective variables. I mean, they will not be transferable as maybe within the particular parameterization, but they should be transferable in their formal nature, because this is at the heart of what theoretical theory development, of course, is. This is the representation of complex systems in terms of theoretically quantifiable properties. And so being able to reduce complex dynamics to a limited number of conceptually related or informally related quantities is really, I think, a very big goal. That does not mean that in the specific applications we will have to include variations of that theme. But I think I just want to I think previous speakers here have already made that point. But at least from my side, this is a very important challenge. Just like, and I think nucleation theory, of course, is one example. But I mean, you can look at all areas of condensed matter physics, soft matter physics, biophysics. There will always be the aim to reduce a complex phenomenon to a limited number of degrees of freedom, and I think those will be, if well chosen, are good starting points for collective variables. Thank you.
Yeah, but I will get back to all of you regarding this one point that was raised, and that was how do you then ensure that you have missed some very important collective variable in your description? So what are the telltale signs? Is there anything general?
Hysteresis in free energy calculations.
Yeah, well, this is where enhanced sampling is most useful to understand if your collective variable is bad. So this is actually my, so it's a very, very easy to see if your collective variable is bad because your free energy calculation will never converge.
So Alessandro, then I would like to make a point that it's not true for all sampling methods, like like Amish mentioned, in umbrella sampling, unless you're willing to start from different sets of windows, you might not.
Well, you're actually right. There are cases, in fact, like let's say one seems to converge even if your collective variable is totally wrong. This I definitely agree.
But in many cases, these distributions won't converge easily. So you will see that the distribution is shifting in these cases where the umbrella sampling simulations where you have forgotten the orthogonal series or not.
Well, you know, so the thing is, well, this I use actually as a, so this of course it depends on how we are doing things, but if you don't really allow the system to make even a single transition in the transverse hidden degree of freedom, your free energy profile will look perfectly converged, perfectly converged.
Right,
and
those are extreme cases, but those are extreme cases. But in a typical situation of a biomolecular system, you always see these.
Yeah, especially if you are using one or umbrella sampling together with other things. In fact, what you are doing, which is combining it with, like, for example, with metadynamics along other collective variables, is a manner of, in a way, helping the system to move as much as possible in the transverse direction and, yeah, improve convergence and monitor problems, no?
Yeah, that's right. But it can be seen, typically we have seen in all umbrella sampling simulations that the distribution converge, you know, I mean, they seems to shift. And I mean, yeah, so that is kind of an indication, and we have seen that consistently in many of these problems.
Okay, I think we have covered quite a lot of ground. And I'm going to hand over the next part of the discussion to Alessandro. Would you like to take up the next part?
Fine. Actually, so there are still, well, actually, there are few things that still I would like to talk about concerning CVs, but I think we have to move on because otherwise we will dedicate all the all the brainstorming session to collective variables. Well, actually, I wanted to move a little bit on, well, the relationship between what we are doing and experiments, because this thing, okay, so it's something that is a little bit of a, it sounds like a trivial point, but, well, some of you have actually written some very, very interesting points on the common document where, which I would like, so I would like really to hear some comment from you. No, like for example, here we have point 3. Well, should experimental results always be considered a dogma? And in particular, so are we aware of, I mean, errors induced in the simulation by the fact that one attempts to reproduce an experimental number, which is then wrong? I am personally, so in my personal experience, so this thing happened to me, I would say 2 or 3 times. The most important one is when we were trying to reproduce the permeation coefficient of a molecule through a membrane, and we have been fighting for a year to get an experimental number, and then we realized that so we had then good evidence that the experiment was actually wrong, no? So here I don't know how many of you had actually similar experiences of spending a lot of time maybe with a poor PhD student and then discovering that the problem was not only in the accuracy of your description of your force field, of your free energy calculation, or of anything, but also of the fact that the experiment was not totally accurate. Any comments? Maybe Jagannath? Yeah.
Yeah, actually, I think Protus might also have similar comments, but as you are trying to point out that when you are trying to beating the boost to figure out whether our result is good, and we are basically trying to figure out how good is the match with the experiment, and at the same time what we don't introspect is that how much uncertainty we should expect in an experimental result. And I think this discussion we had many times, at least myself and with Protus. And he had, multiple times pointed it out, and I have seen that. Let us say you are looking at, off-rate constant for a protein ligand unbinding process. Okay, we are looking for the dissociation off-rate constant, and there has been report for the same system. The numbers can vary between two different experiments, almost 3 orders of magnitude actually. So in that case, let us say you are trying to use whether Markov state model to infer the rate constant, off-rate constant, or even try to use the metadynamics like infrequent metadynamics to infer the off-rate constant, you might end up with something which is in between the reported experimental values from 2 different or 3 different experiments. And then you do not know whether the series that you have chosen is basically should be guided as such that your result is matching with one of those experiments, or should you choose one of those experiments at which your result is matching and then just be happy with this. So that has I have seen multiple times. Many of the systems that we generally see, the off-rate constant for dissociation constant of ligand unbinding is quite different from what you generally find. You can always argue that maybe the sampling issue, maybe the force field issue, but at the same time, experiment also has quite a lot of errors actually.
Thanks. Pratyush, you wanted to say something?
Jagannath already made my point, so I recuse myself.
So Gerard?
Yeah, thanks, Alessandro. I think this is the point you raised is a very, very important one. And I mean, 2 comments. First, my impression over the last maybe 5 to 10 years has been, particularly, let's say, in terms of protein molecular dynamic simulations, if we see some instabilities, this has often been not the problem of our force field, but problem of with initial structures given to us. So I think that I at least remind my group, if your simulations consistently show behavior that is inconsistent, you should take it at least serious and maybe revisit the experiment or whatever the initial structure that you got. But beyond this kind of anecdotal point, I think the more important question is how do we trade off different sources of information? And we saw this like today in Cecilia's talk, and so I think yesterday in Peter Bullhouse's talk. We and others are establishing frameworks, for instance, Bayesian frameworks, where this can be done in a more formal way, where questions like what Pratyush and Jagannath just brought up, that the rate constants can be included when you have not just Gaussian error models, but you do allow for the possibility that there's a faint chance that, but not zero, that they really have not measured in the experiments what they claim to have measured. And so then if you think about the problem in these more general statistical framework, it becomes tractable, at least in a formal way, that you have something that you can rely on. These are not arbitrary decisions anymore that you have to make. Of course, in a specific case, I mean, this is very sad what you described, and I think we, in various aspects and variations, we have made similar experiences, if not, maybe, hopefully not quite as dramatic. Alessandro.
Yeah. Well, in a way, I think on the positive side, I definitely agree that there are at least some cases where we have learned to trust more our simulations than experiments, and the stability of a protein structure is an example, in my opinion. I'm really talking about plain stability, like you take a globular protein, maybe this is stabilized by some folding cofactor they have added, and then this moves. So this actually is very, very important and very relevant, because actually it's something that was very different years ago. No, so this is actually where we see things moving. No, so if you compare, so maybe the same question, so like 15 years ago already, we wouldn't have been in such a situation to be so trustfully of the force fields to say, okay, if this is drifting, there must be something wrong in the crystal structure, right? So maybe now, Amish, I don't know if the hands appear on my screen in the order in which they have been raised, but I assume they are. Amish, please.
So I wanted to make 2 points. One is that we're often interested in problems that are tipping points, right? They're near phase transitions, because you turn a knob and then you see some dramatic transition, right? Whether it's protein denaturation or any crystal nucleation, things of that nature. And a lot of complicated problems, we don't always realize that we are near these tipping points, right? And so sometimes when we see these drastic differences between what we observe and what the experimentalists observe, it may just be that, we're just a little bit away on the x-axis, but we're measuring on the y-axis is very different, right? And so a lot of times, sort of systematically perturbing the system and looking at its behavior, which we can do readily, much more easily perhaps in the simulations than the experimentalists can do, and seeing, how far away are we, from being able to look at the experimentally observed behavior might sometimes be very instructive.
Well, so, this is actually something which can be done in a formally clean manner in Bayesian inference. No, so basically, how large, how strong should your prior be in order to bring you to a distribution which is consistent with experiments? No, so this thing is, of course, if you make your prior like a solid rock thing, then you will always manage. But this is, in a way, Bayesian inference has actually strongly advanced at least our capability of quantifying how really far we are from experiments. No, so because from time to time I agree with what Amish said. Even if it looks like you are far, then you just change your conditions a little bit, and then you are on top of that, and this thing can be indeed quantified, and this is actually good news. Gerhard?
Sorry, can I make one more point?
Please go ahead. I thought that
the second point that I want to make was a little bit pernicious, perhaps. A lot of times what happens is that the experimentalists sort of, all of us as scientists, we try to, take our system and make a cartoon version of it based on what we think is going on. As an experimentalist in a previous life, I know that experimentalists have to do this with even less data, or much less data than we do. And so a lot of times they come up with a cartoon of what they think the process that they're observing is, the key process that they're observing. They come and tell you that. And if you trust them or take that at face value, sometimes you can spend a lot of time studying that process, right? Which is, a sort of, and you may have a good representation and understanding of that particular process, but that's not the key process that's going on in the experiment. It's something else that the experimentalists perhaps haven't realized is much more important to their observations, right? And so in these cases, I think it really, there is no other option but to have a really tight integration and have, and understand exactly what is going on in the experiments before investing a whole lot of time and effort into our simulations. And I think that perhaps is a lot easier said than done, but it can, in the long run, be perhaps a big time saver. Thanks.
Okay, Gerard, maybe?
Yeah, I think I'm agreeing with Ash, really. What I was going to say is, I don't think we should use this language of, are we reproducing experiment or not? Just reproducing experiment is not particularly useful unless we're adding to the interpretation of the experiment. Then there is no point doing the simulations. And maybe that added to the process of adding to the interpretation of the experiments is saying, well, our simulations don't agree with the experiments, or whatever else it is. So I really think we should get away from that language of reproducing experiments, because it's not enough.
I really agree on that. While I didn't agree on the think of collective variable on this, I really agree, but maybe I can let Shrabani comment on that.
Actually, it's absolutely true, but as you see that the first set of hypotheses about a given process comes from the experimentalists, because they are the ones who are designing the variations of the experiments. So obviously they have a hypothesis to start with. So I think enhanced sampling can help in identifying some missing pieces in that puzzle, definitely, and complete, within quotes, complete the picture, and instigate new experiments, and that would be the best contribution. But at this point, I would also like to mention that our sampling in this discussion part is mainly focused into the CVs concerning the PIs, and we are missing a huge subspace of the other participants who are keeping absolutely mum. So let's have an enhanced sampling of that population. So the students and the other practitioners, postdocs, please, we would like to hear from you. So please raise your hand. And as you understand, no point is a silly point or a stupid point. Maybe we can learn from you.
Yeah, maybe while I agree that it would be great to have younger scientists, participant to take part. So I don't know, maybe there is still a raised hand by Harish, I think. Please, Harish, go ahead.
Thank you. I can add something to the mix, I guess. Here in the experimental observation, I think. So fundamentally, like, there is no reason to believe why an experimental measurement cannot be robust. Like, we believe that a simulation may not be robust. It's a function of, I think, who is doing the experiment and who is doing the simulation, and how carefully the measurement is done, and how the robustness of the observation is made. And if I go another step further, I would say one should only believe the things that one does firsthand, whether it's simulation or it is an experiment. Unfortunately, it's difficult to put it into practice because not all of us are trained in all kind of techniques, and not have the freedom and the ability to test our ideas both ways. So concerning biomolecular system, I would just say, many a times, I guess, the inconsistency between experiment and simulation could come from ensemble measurement versus the single molecule nature of work, I think, sometimes done in the simulations. So experimentally, it's very hard to do single molecule experiments and really precisely control the condition. And that's why precisely, I guess, we have the simulations to help us isolate, I think, variables and more carefully probe them, I guess, in a simulation setting. So my 2 cents, I guess, on this.
Okay. Maybe I would also like to touch at least briefly upon another point which was raised by Suman. Suman, maybe you can ask directly to the audience about, yeah, you have raised two important points about where we are. Like, maybe I can do it directly so we save some time. So
yeah. So basically,
where are we?
Hi. So I just made a follow-up point in the document that while we try to reproduce and interpret the experimental results, it might be crucial to also mimic the experimental conditions. So and that sometimes can be tricky. So how closely you can mimic the experimental conditions under simulation settings, and how much important that could be. For example, pH, buffer, salt, and so on.
Let's focus on a specific case, because you raised, of course, many points. For example, pH.
Right.
So let's say that we talk about pH.
So how to assign protonation states of the protein.
Which means actually protonation states. So here, since I am in this this business now, I'm actually not really anymore in this business, but so I've been in this business for a pretty long time, in the business of molecular simulation, for almost 20 years, modeling appropriately the protonation state of amino acids has always been an issue. And I haven't seen, so I have seen, so where are we at the moment concerning this? Do we still think, do we think that, so now there are, well, there are of course constant pH simulation techniques, but finally nobody uses them, except in my personal impression. Is it because they are very difficult, because they are useless, because we have learned how to fix the protonation state for a given pH based on our experience? What is your impression on that? Maybe somebody doing large-scale molecular dynamic simulation on biomolecules.
The right person to answer that, but I just wanted to tell you that even just do the thermodynamic integration, or just to see what is the protonation state of the one residue is such a painful activity to do, because it just, I
agree.
When we completely forget about orthogonal coordinates when we try to do free energy of different protonation states, otherwise we do all kinds of fancy enhanced sampling. And I guess in that respect, the free energy calculation, the approach which Mark Tuckerman has put forward, where he used CVs also together with free energy perturbation, and also Aaron Dinner has this paper recently. I think, I mean, he talked about that, right, in the RARE meeting. I think that's also is. I think we have to still work a lot, and it's not an easy problem to solve at all. I think, Alessandro, you said it correct. We are nowhere, I think, in this.
Shivani? Shivani?
Yeah, so yeah, I want to add here, like even for protonation states and all those things, we do free energy calculations like thermodynamic integration of free energy perturbation, and there we can also think about sampling, enhanced sampling the slow degrees of freedoms, like I mean this we can think about the CVs and all, and enhance sample that, and also that is also I mean not a easy thing to do. Like, yeah, I mean, if I can get some reviews or comment on this, that would be like helpful.
Okay, so maybe this we can comment. So
yes, actually, Shivani, this is one of the comments that we already have in our checklist. That is a training a part of it. Thank you very much for raising this issue. And yes, so I think we are running out of time, and this discussion, now that Shivani has started talking about from the practitioner's perspective, yes, we could have kept on talking about it. But yes, we will definitely keep that in mind as one of the outcomes of the brainstorming session. Thank you so much.
Maybe you can take, so I still see some raised hand. This is actually a very, very important point. Maybe you, for the very last part of the discussion, we can actually dedicate this last 5 to 10 minutes to this point, which I agree is very, very important. I didn't want, so maybe we can let well, there are still 2 persons with raised hand. Maybe we can let them make a comment, and we spend some time thinking about that.
Yes, Anand, so
Yeah, so I wanted to make 2 points. One is regarding the discussions that already happened with respect to experiments. And one thing that we have to take into consideration is the uncertainty quantification, right? Which some people have talked in this conference. So even in your simulations there, we tend to talk about convergence a lot, but there natural systems like stochastic systems will have fluctuations, and even in the and so that uncertainty is there both in the experiments and in the simulation, and that needs to be kind of brought together and not just say that the experiments are all wrong, or I know none of us are saying that, but in absence of no experimentalists present in this forum, it's an unfair sort of arguments that are being made. It would have been nice if there were experimentalists present here and we would have had a fair discussion about how good our simulations, how much trust have we developed over the last 20, 30 years. We have come very far, but this kind of attitude won't take us closer to the experiments. That's what I'm trying to say. And so that should be kept in mind as honest simulators. That's what I strongly believe in, and I hope all of you would agree to that.
Yeah, I think at this particular point, maybe Gerhard might be the closest to an experimentalist now, considering his large-scale simulation. Maybe he can put a comment on that.
Sure, yeah.
Maybe Tarak as a last comment on this part of the session.
I wanted to talk about the protonation because we are doing some things, and if Tarak allows me 2 minutes, I'll just make that point because Shivani was
please go ahead.
so this is again this again goes back to what Alexandro was saying, and so this is a simple simulation that we did based on some of the experiments. These experiments were trying to understand dissociation constants of how a protein binds, a membrane binding protein binds to inositol lipids. And you know, anisotols like PIP2 lipid can be in 4 different protonation states. It can have 3 ionization states, and actually one of them can have 2 different protonations. So for the same ionization state, you can have 2 different protonation states. And PIP3 can have 4 different ionization states. And for one of the ionization, you can have 3 different protonation states. So now, when you do NMR experiments, like we talk about these different states of the protein, it is possible for the same ionization state, the proton can be in any one of the phosphorus phosphates. And so, there were some very nice experiments in NMR done, where they're trying to find out what would be the populations of these different inositols, like with the same ionization state. And this is very difficult in experiments. And this is where I think simulation can come into a picture where you can then do your individual, because you can actually protonate something and find out the free energy of it, and then estimate the populations of those protonated states, and then take a sort of weighted averages of it and try to see how well you're matching with the experiment. So again, this goes back to the same point, like what Gareth was also trying to say. In the end, by looking into what the experiments ensembled average data is, which is always ensembled average, actually. We have actually the nice thing about making model systems and deconvoluting a lot of things. And so this can be all put together from that. And so we are trying to find out how each of the ionization state, what is the population in a given pH, and then what would be the population average in terms of the KD values that you can get. So yeah, these are difficult problems to do, but this is what I wanted to say about this. Sorry, I took some more time than I thought. Yeah, please.
Yeah, yes, Taruk, can you make it quick follow-up of what Anand said?
I think I'll talk a little bit different thing than what it is more on this constant, mimicking real experimental conditions. So we've been working on this constant chemical potential molecular dynamics, which kind of allows us to keep the solution concentration during nucleation or crystal growth. So that's something kind of mimics the experimental bulk concentration.
Absolutely. So, but exactly, so the thing is the following, that while you can do these things like for studying, for example, phase coexistence, and they are actually very, very powerful, I'm not sure that there is a method which is as effective for protonation state in biomolecules. That was my only comment. Sorry for interrupting.
Than these things. Yeah. So
okay, your network has some problem.
Yep.
Okay, so I had a bit of network issue. Yes, I mean, I agree with Alessandro completely that controlling pH for biomolecular system is much more complex than anything else. In fact, sometimes we even don't know the pKs of some amino acids inside the cavities when they're solvent, and this is something needs more careful and more work, I guess. And if I can ask or comment on rather a different question or topic, is the interpretability of the machine learning CVs. Did you discuss this, or I'd like to know, because many times we combine CVs like distances, coordination numbers, and angles, and then
we discussed this a little bit. I personally discussed for at least 2 hours on exactly this point, and I would actually love to do it. But maybe I think we are we are actually finishing our time.
Yes, so
maybe I would suggest to hear the comment of Amelandu, who hasn't talked yet, and then
thank you, Alessandro. No, I just wanted to make a quick comment regarding this comparing with experiments, and particularly in the context of your protonic states. You are primarily thinking of like comparing with experiments which look at your free energy changes or perhaps the rate of a chemical reaction. But we could also look at many of the spectroscopic results, particularly in the context of protonic states, because many of the these multidimensional spectroscopic experiments, they have been actually looking at this proton transfer kinetics, the existence of various protonic states, their interconversion, and so on. And those experiments typically people don't doubt. I mean, they're pretty accurate. Okay, so that way we can take those spectroscopic results as some kind of benchmark or reference results, and then try to see what this machine learning or these rare event methods could say to arrive at those spectroscopic features which are available, in the literature. As of now, I think most of those multidimensional experiments, I mean spectroscopic experiments, they have been looking at perhaps relatively fast processes, where they're not that slow. But nevertheless, I mean, slowly, like I think those experiments are also looking at this these slow conformational transitions in proteins and in DNAs. Also, even as slow as like your amyloid formations and how they can be captured through your spectroscopic signature. So perhaps that could be another area to look at how these rare event methods, including machine learning, could be connected to your spectroscopic observables, because those experiments are typically taken to be fairly accurate. And yeah, that's okay.
I strongly endorse this comment. I agree that spectroscopy is still a very, very trustable benchmark, and for sure, more trustable than other stuff. So maybe I think we are really running out of time. I would like really to so there are still 2 people with the raised hand, and I would ask them to make their comments, and then maybe we can close this very interesting discussion. Maybe I think the first to raise the hand was Tarak, please.
I don't want to take much time, but as I was kind of looking at the last point. Is there any other question on MD-based approaches apart from CV discovery, where machine learning-based approaches can be turned useful? So I was thinking if we can I don't know, it might be a vague question, but can we deal with electrostatics with, let's say, instead of using the electrostatics, what we do every time step or whatever, we can train a neural network, get the electrostatics from there.
The answer is yes. There are several attempts of attempting to train a neural network to predict Ewald stuff, and also for the polarization, I'm aware of many other things. So these are things that were not strongly covered in this workshop because it's about rare events, but there is a lot of work going on in developing force fields.
Okay, probably I missed those works. I'll check it out. Thanks, Alessandro.
You can, I can, send you some references if you need.
Sure. That would be great. Thanks.
Shivani?
Yeah. So talking about the protonation states and all. So if we have suppose we have a protein and we want to find out the protonation state for a particular residue, that is itself difficult, or but it becomes more difficult when we have multiple residues and we don't know the protonation states of 2-3 residues. So how to deal with such problems? Any comment on that would be helpful.
Yeah, well, in fact, so this is exactly the point that I was making. So in my personal impression on that very difficult problem, we didn't move very much in the last 20 years, in the sense that, so I'm personally aware of methods which allow doing constant pH. Yeah, but they are complicated. They are very complicated. So this is actually still, in my personal opinion, an open problem. All right. So maybe now, Gerard, maybe you can close the discussion, since you have made the fatal mistake to raise your hand in the wrong moment. You can say, Gerard, you are gone. So
So I'm not going to make then the comment that people old enough will remember that the null model was always the best predictor of the protonation state, which is just to take the pKa of the residue in solution. It beat all the prediction models for a long time, but I'm sure AI will do better one day. But I think if I'm the last questioner, all I would like to say is, this was a truly amazing meeting. And I mean, I have had the sad pleasure of attending quite a number of virtual meetings, and this was a truly great one. I think I can only say, organizers, you did a fantastic job leading up to the meeting, getting us all excited and getting us through the meeting. And I think all I can say is, it's so sad for me not to be with you in some beautiful location in India and having all these informal discussions, which would now be happening. And I think we would be discussing collective variables for many more hours over many good beers. But we will do this next time, right?
Yes. We will
get rid of this virus now.
Yes.
Yeah. We count on that, really. I really want to also, well, not only virtually clap hands or, like German style.
Right. Thank you so much, everybody. I think I thank Srabani and Alessandro. I mean, this is really the heart of rare meetings. These sessions, we used to have 2 brainstorming sessions. Actually, what happened, we had almost all the speakers in the speaker list was not dynamic this time. So I was telling Srabani that we are not inviting you until the last moment because there's no space to keep all the speakers, and that is really it was a great honor for all of us, actually. Thank you so much, Alessandro and Srabani, for doing this really difficult job. And if all of you permit, I will just take 2 minutes just to thank everybody. Are you able to see the screen?
Yeah, we are.
Yes.
Yeah.
Yes.
I have written down a few points so that I don't miss anything. So again, thank you so much for wonderful discussions and being joining this at very odd times. So today morning we had somebody at 3 a.m. from Europe attending the sessions, and I mean it's really great encouragement for all the organizers, and it's truly, I mean, it's something for us. And I would like to tell the youngsters that the poster session was very good. I mean, it's sad that we're missing that physical touch. You will be sent the participation certificates very soon. Our office will be creating them and will be sending it to you. For all the updates of the meeting, please visit this Twitter. So any follow-up discussions will be on this Twitter page. And in the YouTube channel, you will be able to see all the lectures. We are editing each of the lectures, and that will be available to you. And I would like to thank, on behalf of all the organizers, IUSTF, Indo-US Science and Technology Forum, which has been supporting us for all the 3 RARE meetings. The first RARE meeting was in 2014. And then 2017, and this they have been really liberal, and they've been supporting 10 participants from US, the full airfare, which is quite a large amount of money, and support from all of you supporting this meeting. To start with Mark Tuckerman, who really came forward in 2014 meeting and said that, okay, this is a good thing that we, our community should work together, and we should bring a lot of activity in this field, so this meeting would help. And also, I should say that this meeting has also resulted in several other collaborations. Several of us are involved in collaborations because of this meeting, and it has also helped us to do some workshops for the students. And we have been successful a couple of workshops in this respect, and we'll be doing more in the coming years. And yeah, so this was what I was trying to say. Again, I thank all the previous PIs of this project, Mark Tuckerman, Christopher Yadzinski, Srihari, Pratyush, and myself. We are constant in this dynamics. And Jagannath, we convinced him. I will show you how we convinced him in a short while. So this is the 2014 photograph. It was a very small community, and it was on the beautiful location in Kerala, on a lakeside. And a lot of people, you can see that they are also here in this meeting also. And these are, like, you can see Alessandro having some beer as soon as he landed, and we had wonderful food, and Sravani giving talk on proton transfer. And we had a boat trip, and Srihari was talking about rare trajectories, talking about, so if he's completely against collective variables in Cartesian coordinate space, he's talking about momentum space. So we had like really fantastic discussions. And then the meeting, the group really expanded. You can see the photograph is widened, and that's really showing success of this meeting. And I hope the next meeting will be more successful. So, and we were fortunate to have really the stalwarts of the field in this. And yeah, you can see it was a very lively meeting, and Gareth is enjoying beer. And I mean, you can see the non-equilibrium dynamics here. And this was, I think we hitchhiked on some auto rickshaws, went to a beer place, and had, I think the shop was closing. Then we kind of gave some extra money and got the shop opened and drank beer at late night, and that was also fun. And this was how we convinced Jagannath to be part of 2021. We gave some beer, some money, and a lot of discussion. But now, Jagannath, you will be also conserved in the dynamics of RARE.
Yeah, I'll be very happy to be here.
Right, and yeah, it was really something, some good meeting. And so 2021 was equally exciting. And I will share some of these photographs with you. And you can also visit the YouTube channel here, and also photograph links will be also shared on the Twitter page. And we don't know where the next RARE will be and how it will be, but we try to make it will be a physical meeting. And I would invite all of you to be part of it. And I think we should just discuss on collective variable on one full day and get the things sorted out and write a review or a discussion article or something like that, so that the students also learn about it actually. So, and thank you so much. And if I give it to Jagannath, Jagannath, would you like to add a few points?
I think you have pretty much covered most of it. I just would like to, acknowledge that we had really good number of student volunteers, especially from Nishan's group, who actually, made sure that the conference is socially advertised in social media, and they did a really fantastic job.
I'll just ask them to come.
Yeah, and they actually made sure that in all the YouTube links and everything is already there. And I personally think this is the amazing feat, because they are all awake all the time and try to do the job. And that made our job much easier, I think. So, I personally, it has been a learning experience for me. And, like in 2017, I think when I was there was about 2 talks, which was on neural network. And now in this particular thing that I'm finding that everyone at least had one slide with one neural network. And I'm really learning a lot, and I'm really happy to be part of this network actually.
Pritish?
Yeah, I mean, I was wondering as to how many RAREs from now will it take that half the talks will be about quantum computing. I think it's going to happen, believe it or not, it will happen sooner or later. But yeah, it's been amazing. I especially want to thank Nishan, because Nishan for me has been like the real force behind RARE. I think we can all
I also agree on the same.
And really going for it year after year. So, and yeah, I mean, it's wonderful to see all of you. I mean, I don't think there would be any other workshop where we would have a session on the 5th day. For us, it's the 5th day in the United States, and 43 people still attending till the very end. So thank you all for staying till the very end.
Andrew?
Yeah, thank you so much to everybody. It's been a real pleasure organizing this, and yeah, big applause to Nisant and his students for really pulling together all these things. The technical challenges were not trivial, and so hopefully we can be together next time. But one of the nice things, I suppose, was to be able to record and live stream this thing. I think it's really sort of democratized that and allowed many more people to participate who might not have been able to otherwise, and also sort of memorialize that with the videos. And so I think that's one good thing that's happened, and perhaps we can try and maintain that for the next one. So yeah, thank you everybody. It's been really wonderful, and hope to see you all for the next one.
Yeah, I will now ask Amalindu to speak. Before that, I should say that Amalindu has been such a great supporter of this meeting. I mean, the first meeting would not have happened if he was not there. I mean, he was the Dean of Research and Development at that time. He kind of really helped us moving, and then he has been always there, and he took this so to say PI of this project when he was extremely busy. So now he's a little free, but he was really busy, and then he spent a lot of time with us. And Amalindu, please. Yeah.
Okay, yeah, thank you, Nishan. So let me thank all of you for your support, for coming forward and making this event an enjoyable and fascinating one for all of us. Thank you for your participation. And from my side, of course, I mean, my name was there sort of an official PI, but it's a Nishant and Jagannath. I'm talking about the Indian side. Okay, so Nishant and Jagannath did everything, and I sort of just enjoyed things. Okay, staying in the background, and most of the times, although I was listening, but most of the times I was just switching off my video and sort of and enjoying the talks. So thank you, Nishant and Jagannath, for sort of taking care of all the logistic issues, and also thanks to Nishant's students, and of course, I must thank Patush and Andrew. Also, we had a number of meetings over Zoom, and it was quite enjoyable, and I really enjoyed working with all my co-organizers. And thank you all again for coming forward and for your participation in the meeting. We really had a wonderful 5 days of meeting, and we shall look forward to the next meeting, which should be in 2 years' time from now. And we hope we will have it at a good location in India, and we hope we'll be having a physical meeting at that point of time. So yeah, so I think that's all. Thank you so much. Thank you.
You updated on that, and yeah. Thank you so much. So time to say bye. And yeah, thank you.
Can you take a picture, Nishan? So we have
Yeah, yes.
ISTF actually also needs a picture from us.
Right. Yes, if all of you can switch on your camera, great. Yeah. Thank you. Yep. Thank you, everyone.
Bye.
Thank you. Bye-bye.
Thank you.
Thank you. Bye-bye to everybody. It was great.
Thank you very much, everybody.
Bye.
Bye.
Ciao a tutti.
Bye, everyone.
Bye.
Bye-bye.
Bye. Thanks all.